Hi there, and welcome to Unit 2, Dynamics and Uniform Circular Motion, and our first video lesson. So in Unit 1, we focused a lot on setting up a lot of our background and constructs of how we quantify and describe motion. And we led us to all the kinematic equations and a few different interesting applications such as projectile motion to quantify. Now in Unit 2, we're going to dive into a different way of analyzing motion. And when I say the concept of dynamics, that means we're taking a look at forces. And what forces cause, as we'll talk about later, is acceleration. So we're taking a look at one piece of what we talked about already, the acceleration piece, and trying to understand where exactly that comes from. Additionally, at the end, we will be covering this concept or talking about this concept of uniform circular motion. And with uniform circular motion, that's just that. It's an object that goes in a circle with a constant speed, and we'll talk about some of the implications of that. Now, a little bit of quick background on dynamics. Dynamics is specifically the branch of mechanics concerned with the motion of bodies under the action of forces. Now, mechanics literally just means it's the quantification of motion. So last time, kinematics was by taking a look using kinematic equations and understanding acceleration and velocity and those things. So we use those to quantitatively describe an object's motion. Dynamics is using the forces acting on them to solve for the acceleration component of that motion, and then we can take that back to kinematics to make additional observations. So really, this is an extension, or you could say that the more intricate or next step in what we've already talked about. So we're going to start by taking a look at the biggest name in physics, but the biggest name associated when we talk about forces. And we're going to start by looking at Newton's laws. Now, Newton has three laws that govern dynamics, and we're going to take a look at each of those throughout the course of this unit. In this first pre-lecture video, Brian Jones starts with a simple demonstration of applying a force to an object. And in that force, he's using this hacksaw blade that you can see in this actually right there. And he's letting it bend to a certain amount to try to measure that force. And this pickup truck over here, it undergoes some motion. And he makes a free body diagram, and we see that indeed we have a force being applied that causes acceleration. And more specifically, it causes a constant acceleration, which we've already talked about as being non-uniform motion. So the first big demonstration is just that. It's solving for a piece of the puzzle that we've already talked about by looking at what causes acceleration. Then he adds more mass to the truck. Now, in last unit, we talked nothing about mass, absolutely nothing about mass. But now, in this unit, we're going to have to take that into consideration when we take a look at the forces that are being applied to an object. And then after the truck experiment, he gets into a little bit more about talking about how forces are an interaction between two objects. And then he goes on by demonstrating a couple of things with these spring toys. So we'll talk a lot about Newton's third law, which all forces occur as part of an action-reaction pair, and how if I push on to something, it's pushing back on me. But he kind of preludes that in this first little pre-lecture video. Okay, so the very first section of this chapter is taking a look at motion and forces. So how is motion related, or what causes motion, and how it relates to forces? And that's the first thing we'll take a look at. Okay, so we can ask ourselves the question, what actually causes motion? In last unit, we just said, hey, motion's happening. Well, let's take a look at this quick little example. In example A, we have a student, or a student doesn't have to be a student. We have a kid on a sled, and that kid on a sled, if he's on a sled on some smooth snow, the sled will come to rest. And we've seen, you probably have gone sledding, and you go down to the bottom of the hill, and your sled comes to rest on its own. But if we think about changing this concept, and instead we're going to go on some slick ice. So maybe you're sledding by the lake, and then your sled goes onto the ice, and it might go quite a much larger distance. So on that slick ice, the sled slides further. Now, if I think about in physics, we always talk about like a frictionless surface, and a frictionless surface means just that there is no friction. And if friction could be reduced to zero, the sled would just keep going and going and going and never stop. So in the absence of friction, if the sled is in motion or if the sled is moving, it will stay in motion. And that'll actually bring us to Newton's first law. Newton's first law is that an object, if it has no forces acting on it, then if it's at rest, it'll stay at rest. If it's in motion, it'll continue to stay in motion at a constant speed. So Newton's first law we often refer to as the law of inertia. An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless an outside force acts upon it. That's the simplest definition of Newton's first law. And it means that if there are no forces acting on something, then something will stay in motion or it'll stay at rest at a constant speed. A little historical significance, Aristotle was actually the one who initially said a force is required to keep an object in motion. And if I think about that, that actually kind of makes sense too, because if I'm pushing a fridge, for example, I need to use a very big constant force just to have constant velocity. But in reality, that's not the case. I'm actually overcoming friction the entire time. So Newton was the one who said, no, that's not quite right. And then he came up with some laws of motion to help explain and describe what is actually going on. So we have to ask ourselves then, if we're talking about Newton's first law and we're talking about forces, what is a force? No, I am not a force. I am your teacher. So please stop calling me that. But anyway, a force is a push or a pull on an object. It's a very simple definition. It's a push or a pull on an object. Every force has its own agent or something that acts or pushes or pulls on it. So in this, we got this track athlete over here. She's got the shot put, and she has to push the shot put in order to get it to move. Now, that shot put, of course, will in fact follow a projectile motion, as we have previously discussed, but something has to get that initial velocity. So the agent is the person that's doing the force. So here we have a football player. He's the agent on the football. And then we have an object, and that's something that's receiving the force. So we'll categorize those two things as we talk about forces. Now, forces are a vector quantity. So it means that it has both magnitude and direction. For forces, we use a capital letter F, and the magnitude is just the letter F, but as you'll see, I try to be consistent, and I use this little vector symbol at the top of it, because that would be the correct way of making sure that we know it's a vector. And we'll take a look at a couple different types of forces, but really they fall into two different categories. We have contact forces, which literally means that, yeah, the force needs to be contacted, or it's something that's physically pushed or pulled through touching at a point of contact. But we'll also take a look at long-range forces. And forces that are long-range forces, they're forces that they act without physical contact. And there's a few different categories of those that we'll talk about. For example, gravity, right? Gravity is always acting, even if I'm hundreds of feet into the air. It's a range force. We think about magnets. Magnets attract each other or repel each other, and we feel that from a distance apart. And we'll also take a look at electric charges, and we'll actually come back to that later in the year in our last unit. All right, so when we take a look at a force vector, we got to think about the easiest concept is thinking about how we're applying that force. So in this first picture up in this corner, we have this nice little representation. Here's a box, and this person is pulling on the box. Well, if the box is the object, we represent it with a single point. and then we draw the force acting in some direction. And we'll come back to this concept. This concept is known as when we draw a free body diagram. But we represent the object as a particle, and we just draw as a force leaving that particle the direction of motion. Now, or the direction that the force is applied. Now, this can be confusing because this person is pulling. So some people might say, well, isn't the force kind of on this rope? And that's not correct. The direction that we look at is just based on the direction of the object, and that object is being pulled to the right. In the second concept, we're taking a look at a box being in the air. So then gravity is going to pull it straight down, and Earth is acting as the agent, causing that range force of gravity. We also will label each of our forces. So here, this is T for tension, and we'll build a catalog of forces very soon. And then here's W for weight, aka the force of gravity. Now, I can also have multiple forces acting on one object, and this will get us into Newton's second law, which we'll talk about a little later. But for example, if I had, we'll call it a teddy bear instead of a box because it makes more sense. If I have two people pulling on a teddy bear, one person pulling straight down, one person pulling up and to the right, there can't be two directions of motion unless you rip the teddy bear. So when we simplify this with the force diagram or the force vectors, we have the particle for the box. One person is pulling down, one person is pulling up and to the right, and then I get this net force, which is a combination of those two forces, which is in this case down and to the right. And we can get into some really tricky problems that deal with forces acting at angles. We got to break everything down into components, and things can get very, very confusing. Now, we'll take a look at some of those problems, but we'll actually keep it relatively simple as we go through this unit because we're getting the overview and we're moving on. So I got a quick check for you in the notes, and we're taking a look at two forces acting, and if we had a third force to cancel it out, so here are our two forces that are acting in this corner over here. If I have two forces acting, what force would cancel it out? And in this case, I have a positive y component and a positive x component, which means to cancel it out, I need a negative x component and a negative y component. So the answer is this force right here, because that force is pulling down and to the left, which gives me my negative x and negative y component. And that, at this point, is all we're going to really introduce with taking a look at forces. Now, where we go from here is now we got a quick little introduction to forces. So now we want to build a catalog of forces and think about what types of forces can be acting on as an object. As always, we have to start with the explanation of things before we can really get into the quantification. So we'll start by taking a look at an easy way of approaching that, and then later we will add the quantification piece. And we'll start that in the next segment by building a catalog of forces. All right, so now that we've built a short catalog of forces, now we want to get into taking a look at physical situations and identifying forces, and then we'll use these eventually to quantify later. So whenever we identify forces, we have a nice little cheat sheet over here for you about what all the forces are. And then of course later we're going to add formulas to that, and we'll try to put together a nice little list of that as well. But the very first thing that we want to do is we want to identify the object of interest. So whatever it is that we're examining, we want to know what it is. We draw a picture of the situation. So we take a look at it and we see, draw the physical picture of what's going on. And the next kind of 3 and 4 are kind of just thinking about isolating what we're talking about. So drawing a closed curve around the object, because the only thing that we really care about is what is happening to the object. We don't care about everything else that's going on around that. We call that essentially identifying the system, and the system is what we're identifying and isolating to talk about. And then we locate inside of that curved object, we locate every point on the boundary, or if there's other things touching, and we'll talk more about that later to see if there's contact forces. But then we name and label each of the forces acting on the object that are short range or contact forces, and then we name and label all the long range forces acting on the object. So similar to when we set up problems for kinematics, now we got to just be a little bit more specific. There's a little bit more going on when we're identifying forces. So let's go ahead and try an example. So here's our first example, identifying forces on a bungee jumper. So we have a bungee jumper is left off of a bridge and is nearing the bottom of her fall. What forces are being exerted on the bungee jumper? So as best I can, I want to draw a physical situation of the object. I think when you bungee jump that you have a cable that's kind of tied off to your foot that's like stretching out. So all we care about now is we care about what's going on inside of all this right here. We don't really care about the rest of the bungee cord. We don't care about the rest of the world outside of it, but that's it. So we have contact forces that we're identifying, and the contact forces, well, the person is having a bungee cord, and the bungee cord is stretching, so there is actually a spring force going up, and that is all. And then the only range force is we have the weight going down. So the gravitational force will be going down, the spring force is going up. And as we look at this picture, very similar to what we talked about. The only difference is, and this is sometimes interchangeable, and we'll talk about that as we get through different examples. I identified here, we identified a tension instead. Now, tension is by a rope. I think if it's a bungee jumper, it should actually be like a bungee cord, which stretches, and that's actually more like a rubber band or like a spring force. So in this case right now, we're just identifying forces, so either one is totally fine. One more example problem we have is identifying a skier is being towed up a snow-covered hill. So if anyone's been skiing, there's a lot of times on the bunny hill you get a tow rope. So if I can go ahead and draw the person, take a moment to try to draw the person going on the hill, and pause the video and see if you can identify the forces. So if you were correctly able to identify the forces, you would know that there's a tow rope that's providing a tension going up the hill. And then other than that, there is weight of the person going down the hill. But what you probably forgot, because it's a very, very forgetful thing, is that there's also a normal force of the hill pushing back up on the person. So if we talked about the normal force when we identified our identifying, making a short catalog of forces. The normal force is, it's called the normal force because it's perpendicular to the surface. So the skier pushes back down on the hill, so the hill pushes back up on the skier. And then the last one, I would call this one kind of more of an optional one, but I think it is a fair one to include, is kinetic friction. So we have friction opposing motion, and because the object is in motion, then we have kinetic friction acting on the object. So this was just a really quick and easy exercise in identifying forces. Where we go from here is now how do we organize these forces so that we can understand the motion of the object, and that'll get into free body diagrams, which we'll talk about in a later segment. So now that we've built, again, a catalog of forces and we identify forces in a situation, we can kind of go to the next level as we're working towards quantification and ask ourselves the question, what do forces do? And this seems like a really stupid question for us to be asking so much later, and we didn't start with that, but we're going to get into that a little bit here, and then I'm going to do a demonstration in class that will also back up what we're talking about, because right now your guys' definition of what forces do is just anytime that somebody makes you do something that you don't want to do, you simply just call them a force, and of course that is not correct. So I'm going to do a demonstration in class for you, and I'm going to put a cart on a very low friction surface, as we have used before for the speeding up, slowing down lab and understanding the graphing of motion. And then I'm going to attach a string, and I'm going to tie that string to a series of masses hanging from that string that's attached through via a pulley, and that pulley is going to cause this to have a gravitational force, or the weight pull it down, and through that little string it's going to cause the cart to go that way. And the question is what does it do? And as I manipulate stuff, if I were to graph the motion, graph the position versus time, the velocity versus time, the acceleration versus time graphs, what is physically going on in that situation? And then how does that change as I maybe add some extra mass to this cart, or how does it change as I add extra mass to this hanging mass? So those couple questions we're going to answer during class, but I'm also going to talk about them a little bit right now. So I actually have a series of graphs here that I made during class, and the timelines all kind of match up, and we're only interested really in the first 2 seconds. You can see that there's these big chunks at 2 seconds for the last cart, or for the that blue cart, because that's where I had to stop it before it went off the table. But we can see that for the most part, all of the graphs follow this general shape where we have this exponential curve. And as we saw in the last unit, that exponential curve relates to non-uniform motion. And if we were to take a look down at the last graph, the acceleration versus time graph, we do in fact see that we get this constant positive acceleration. And of course, as we examine the graphs in the middle, we see a linear velocity versus time graph, indicating again that we have constant acceleration. Now, the different lines on this graph, as we'll see when I recreate the demonstration in class, correspond to different setups. So, for example, the red line, which is right in the middle, there's 500 grams of mass sitting on the pulley that's causing it to accelerate. And we'll kind of use that as our baseline. So we have this hanging mass, and it causes the car to accelerate. Awesome. Now, what happens when I change and I put 1,000 grams of mass onto the cart? Well, this blue line, it indicates a steeper slope than the red line does. And if we look back down at the bottom, acceleration versus time graph, which is outlined in red, we can see the blue line has a greater positive acceleration. So therefore, I can conclude that a larger force acting on an object, in this case the weight force, which we'll obviously talk about later, we'll actually do a whole lab on this, a greater force causes a greater acceleration. And then the last situation I have is I'm going to go back to my original 500 grams, but I'm going to triple the mass of the cart. So I'm going back to having the same force as the original situation, but now the mass that it's trying to pull is 3 times as large. And we see on the middle graph and on the bottom graph that we got this much gentler slope indicating a lower acceleration. So we know that a larger force causes larger acceleration, and we know that a greater mass causes less acceleration. So we're going to take a look at a formula that relates all these concepts together. So to give a quick recap, we know that an object that is pulled with a constant force moves with constant acceleration. But then we said, all right, well, how do we affect these things? And we decided that, or we found experimentally that acceleration is directly proportional to force. So if I increase the force, I will also increase the acceleration. We found that by hanging a greater mass. And then we also found that acceleration is inversely proportional to an object's mass. So if I increase the mass of an object, I will decrease the acceleration. And these things, they make sense. If I'm pushing something that's heavier, it's harder for me to push it. So I need to, if I want to get the same acceleration, I need to increase my force. And we'll take a look at these 3 concepts: acceleration, force, and mass, and we'll relate them all together in a very simple formula that you've probably seen before in the next segment. Okay, so we took a look at an experiment and we saw or looked at how force, mass, and acceleration, these 3 concepts, force, mass, and acceleration, how they all kind of influence one another. And these 3 things will come together to give us Newton's second law, which is what we're going to talk about in this segment. So Newton's second law, from our little experiment, we saw that a force causes an object to accelerate. So force causes acceleration, and the acceleration is directly proportional, meaning that if I increase it, it's directly proportional to the force. So more force causes more acceleration. But it's inversely proportional to the mass. More mass, less acceleration. And if we relate all these together, we actually get a very simple equation of acceleration is the force divided by the mass of an object. As we can see, there are little arrows over the top of force and acceleration, indicating that they are vector quantities, meaning that they have both magnitude and direction. And we saw this last unit when we talked about acceleration and velocity, because those also both have both magnitude and direction. So the direction of the acceleration indicates the direction that it's not just necessarily speeding up or slowing down, but the positive and negative direction as well, just as it did last unit. So Newton's second law actually is slightly more complex, in that, really not more complex, but it just adds this F net thing. And a net force is the sum of all the forces of an object acting together. So in the very early part of this chapter, we talked about how multiple forces can be acting, but there can only be one net force because there's only one direction of acceleration. So even if I have multiple forces acting on an object, the net force is the sum, it's the vector sum, so the direction does matter, of all the forces acting on the object. And the acceleration points in the same direction as the net force. Now, one of the misconceptions is that the acceleration then is the direction of motion, or the force is the direction of motion, and that's not true at all. It's just the direction of the acceleration. So anytime we have something like friction acting on an object, friction opposes motion, and the net force and the acceleration point in the opposite direction of friction. And we'll examine those problems a little bit more later. So we have just a couple quick checks. And first one, it says a constant force causes an object to accelerate at 4 meters per second squared. What if I double the mass? Well, according to my formula, we know that acceleration equals the force divided by the mass. So if I double the mass, I am going to halve the acceleration because those two things are inversely proportional to one another. Therefore, I will have an acceleration of only 2 meters per second squared instead of the original 4. A quick little conceptual example, if I have a basketball is released from rest, and this is another perfect example of when we have two forces acting on an object, but there can be only one net force. So a basketball is released from rest, and there's a stiff breeze directed to the right. In which direction does the basketball accelerate? Well, we know that there's a weight force, and that's going to cause the basketball to go straight down. But if there's a stiff breeze, we can kind of think, some of you might think of it as like a thrust or some other type of force, a general force, but technically it falls into the category of a drag force, and the drag force is pushing it to the right, which means that the object itself has a force going to the right and going down, so the resultant will be down and to the right. And we see that over on the right side, where we add these two together and we come up with a net force. And the net force is always in the same direction as the acceleration. Now, if I'm just releasing the basketball from rest, this also is the same direction of motion. But if I were to throw the basketball up from the ground, it would give me the exact same net force that I had initially, except now it's going up. So it's actually in a different direction from the motion. All right, just another quick check. It's a 40-car train travels along a straight track at 40 miles an hour, indicating that it is a constant velocity. And a skier speeds up as she goes or skis down the hill. In which case is the net force, so the net force greater? And our instinct is to say it's the 40-kilogram train car, or the 40-car train car, because it's such a large mass that it has to have a large force. But net force, we talked about with Newton's second law, a net force causes acceleration. So this 40-car train is going at a constant 40 miles an hour. So this is actually constant right here, which means that if I have constant velocity, acceleration is 0. And therefore, the net force is also 0. So with those two things in mind, the skier is speeding up as she goes downhill. Therefore, the skier has the greater net force. We have another quick check. An object on a rope is lowered at a constant speed. Well, if I'm thinking about that, if it's going at a constant speed, that means the net force is 0 and the acceleration is 0, which means that no force is bigger than the other one. So there is a weight force going down and there's a tension force going up. And if there's no net force, these two have to be equal to one another. So therefore, the rope tension has to equal the object's weight. All right, so going back to our equation, we got this equation of the acceleration of an object is equal to its net force divided by its mass. And we know that acceleration and net force are both vector quantities. And no surprise, the dude who came up with all these laws, Sir Isaac Newton, named the units of force after himself. So this net force, the unit for it is a Newton. And if I look at what my Newton is, it's what causes 1 kilogram of mass to accelerate 1 meter per second squared. So we know acceleration is meters per second squared from the last unit. So 1 Newton is equal to 1 kilogram meter per second squared, as we can see from this equation right here. We use newtons anytime that we talk about force. That is the unit for force. Okay, and now we have come to our first partner problem, where we're going to be trying to use our equation. Acceleration is the net force divided by the mass. And I'm going to ask you to try to set up this problem, and we'll take a look at it back in class. So as I read through it, I'm going to help you identify some things, but then we are actually going to solve this, or you're going to try to solve this problem, and we'll talk about it during class. So we have a Boeing 737, which is a short-range jet with a mass of 51,000 kilograms. It's at rest. So the pilot turns on the pair of jet engines, and we got to be careful there because it does say pair, which indicates that there are 2 jet engines, and that'll come into play a little bit later, to full throttle, and the thrust accelerates the plane down the runway. After traveling 940 meters, the plane reaches its takeoff speed or velocity of 70 meters per second, and it leaves the ground. And we're wondering, what is the thrust? That's our question, is what is the thrust of each engine? So the thrust will be the force that it is exerting to get it down the runway. So I do have a little summary of that right at the bottom here. I do have your known variables, your xi, your xf, or aka your delta x, vi and vf. And my goal is I'm trying to find A, the acceleration in the x direction, and the net force. So just a little hint, because it's a pair of jet engines, I'm going to take the actual net force that I solved for, and I'm going to go ahead and divide that by 2, and that'll be the thrust of each engine. So take a look at that problem, see if you can set it up and solve it, and we'll take a look at it during class. And that will actually conclude this section for us. All right, so we've had our first exposure to solving a Newton's second law problem, but we're actually going to backtrack a little bit now and make sure that we can properly set up all the problems. And we did the same thing last unit, where we started the unit by drawing all these real pictorial representations of problems, and then we simplified it with the particle model. And we're going to do the same thing with forces right now. And we started by taking a look at a physical situation and drawing or explaining all the forces that were interacting. And now we're going to simplify it up by drawing a free body diagram and talk about those as a really quick way of explaining the forces acting on an object. So what are free body diagrams? They are the equivalency of a picture or a motion diagram that we did in kinematics, except now we're going to apply forces. And these help us visualize the problem with all the forces, and most importantly, they don't just have all the forces, but they show the directions that the forces are acting. And when we've identified them so far, we've just kind of identified the fact that they're happening, and we haven't been drawing where and how they're happening, and that'll become extremely important as we try to go through and solve problems. So free body diagrams, it's a really quick way, a really easy way of visualizing forces. So here's how we make it. First, we identify all the forces that are acting on the object. We will establish a coordinate system. So we want to make sure we have x and y directions, just as we did with projectile motion. It is extremely important to keep things in the x and the y. Well, now we can take a look at acceleration in both directions a different way, and we got to make sure we have that correctly represented. We'll represent the object itself. It doesn't matter if it's a person or a thing, as a single dot at the origin. So to kind of sum up what we've done so far, we're gonna we identify the forces. We're gonna draw a coordinate system, and right at the center of that coordinate system, that's going to be our object, just as a dot. Okay, and then as we get the different vectors or the different forces that pop up, we're going to draw each of them. We represent each of the identified forces, and so for example, if I know that there's the force of gravity, well, gravity pulls straight down, so I do the force of gravity. If there's the normal force goes straight up, so I do the normal force, and I just identify all of the forces acting. Let's say that the object is moving to the right and there's a friction force opposing the motion. I will draw an arrow to the left. And then the very last thing that we're going to do is we're going to take a look at the net force vector. And the net force vector isn't a force vector, but it is something we want to consider. The net force points in the direction of the acceleration. So on my free body diagram here, I have a net force going to the left. And so what I do is right above, wherever I find a nice space, I put an arrow going to the left, and I label that up here as F net. So I do know that there is a net force. It is moving to the left because I have unbalanced forces. So this is a Newton's second law problem, which we'll talk more about as we start to quantify, but there is a net force going to the left, which means that there is also an acceleration also going to the left. All right, so we have an example problem now, and it's a very simple example problem. We have a book is lying at rest on a tabletop, draw forces acting on the book. So when I identify the forces, well, almost always there's going to be a weight force pulling down on the book, and in this case it's sitting on a table, so I know that there's a normal force as well. I draw the coordinate system, and this gets a little overkill. We don't need to really do this every time. I'm going to just draw it as like a dotted line so that it's not as dark and heavy. And I'm going to in black now, I'm going to draw my object as a dot at the center of the at the origin. Those are my only two forces. My weight force goes straight down. My normal force goes straight up. Now, the length of these arrows absolutely matters. And because although this is just a visual representation, again, I should be able to get a lot of information from this. Now, if I look at a book sitting on a table, I know that it's not accelerating up or down, but I should be able to also tell that from my free body diagram. So because the last step is what direction is the net force. Well, in this case, F net equals 0. There is no net force. This is what we call an equilibrium problem, where the object is not accelerating. So if it's sitting on a table, obviously it's not accelerating, so the forces need to be balanced. And we will talk about more about that in the next chapter. Here's another example. We have an egg is free falling from rest in a tree. Neglect air resistance, draw a diagram of the forces. So if I think about what forces are acting, I know I have weight. Weight is almost always a given. And as I think through this, I can't think of anything else that's actually acting. There's no drag force because there's no air resistance. And actually that ends up being 100% correct, that we think about this as an object in free fall. Well, an object in free fall and a projectile have the same kind of characteristics, that a projectile is an object that moves through the air, in which the only force acting on it is gravity. So in this case, F net is straight down. We just have the weight force going down, and that is, in this case, actually equal to the net force. And we'll talk more about these when we get into solving problems. All right, another example. Now we have a skydiver is descending with constant velocity. And it also follows it up by saying consider air resistance. So if I think about that, a skydiver has to have a weight force acting on them because gravity is pulling them down. And in this case, if I am considering air resistance, which I have to if I know that we're in free fall but with constant velocity, that means that there's a drag force pushing back up on me. And I'm going to simplify this one, and I'm just going to go ahead and say that I'm going to skip my coordinate system. My weight is going straight down. My drag force is going straight up. And if I did this right, F net should be equal to 0, because if I'm descending with a constant velocity, as said right there, that means that my acceleration has to be equal to 0, which means my net force has to be equal to 0. So we'll start to see these patterns as we get into problem solving in Chapter 5. All right, another example problem. A car is coasting to the right and slowing down. Neglect air resistance, draw a diagram of the forces. So if we identify it, of course we will have a weight force. That should always be a given. If the car is not accelerating up or down, then there is a normal force, and spoiler alert, that should be equal and opposite to the car's weight. And if I'm going to the right but slowing down, that means I got some type of friction that is causing me to slow down. In this case, this is the friction of motion, so we'll call that kinetic friction. And the question is, what is the force going the opposite of the friction? And the answer is there isn't one. So let me show you what I mean when I draw a free body diagram. Okay, so here's my dot, my particle. The weight is straight down. The normal force is straight up. And it's moving to the right, but it's slowing down, which means that there's friction opposing motion. I'm going to put that right there, the force of kinetic friction. Kinetic, of course, meaning in motion. And my question I'm asking is, what should be going to the right? So the car is moving to the right. The direction of motion is to the right, but there is no force acting to the right. This is actually complete. My free body diagram that I have right here is all done. The net force, of course, going to the left in the direction of the friction. There is no force going to the right. So I mentioned this before, just because an object is in motion doesn't mean that there's a force keeping them in motion. In this case, there is no force going to the right. All right, got a quick check. So it says an elevator lifted by a cable is moving upward and slowing down. So if it's up, it's moving up, but it's slowing down. That means the acceleration has to be directed down. And if the acceleration is down because it's slowing down as it's going up in the positive direction, that means there must be a net force going down, which means that the force that's going up needs to be smaller than the force going down, and that's how we come up with C. So we have some type of force right here. It's this long. That's going up. That's the tension in the cable. And then we have a force that's this long, much longer, or at least a little bit longer, and that's the weight force. So as you're going up, slowing down, the weight force is larger, and that's what's causing that negative acceleration. Got another quick check. It says a ball has been tossed straight up, which is the correct free body diagram. And of course, we always have to think about just after the ball has left the hand. And in that case, it's actually in free fall. So the only force acting on it is gravity, which means that the only force acting is straight down. And we get D as our correct answer. All right, another quick check problem. We have a car is parked on a hill. What's the correct free body diagram? Well, if I quick identify, I'll have the weight force, I'll have a normal force, and I'll have, because it's parked on the hill but not moving, there's some type of static friction. And we'll talk more about that when we get into friction next unit. Now, how we draw these is all of them are correct in that we have this weight force that's going straight down. Gravity always acts straight down. Oh, wait. That's not right. D is not correct. D does not have gravity going straight down. D actually has some things that make sense because we know that the car is balanced, so it must be in equilibrium, meaning that all the forces are balanced. But what they did here is they broke this and this. These are the two components of gravity, so those are not correct. So D, we know, is not the correct answer as we go through this. Okay, then we also have the normal force, and the normal force is always perpendicular to the surface. So, and it's going straight up from the surface, so that's correct. C is still correct, B is still correct, and A is still correct. And that's where we kind of lose E, is E doesn't have that normal force identified, so that's not right. And finally, we have friction. and friction has to be opposing the motion, which we get in C. So gravity wants to pull it down the hill, and the friction is keeping it up the hill from the brakes or from the parking brake on the car, which makes C our correct answer. So C itself is the correct answer. Now, this might look a little weird, but the reason it works is that there's an X component. If I look at my force of gravity right here, there's an X component and there's a Y component, and those two need to be balanced out. So the X component is balanced out by friction, and the Y component is the Y component is balanced out by the normal force, and that's what keeps this one all balanced. All right, so you got a partner problem that you should try setting up with your partner, and I'll just kind of walk you through it a little bit. And it says, consider pushing a block across the table at a steady speed. And of course, anytime we say steady speed, we know that that means acceleration equals 0. We'll actually do a lab on pushing and pulling blocks a little bit later. Since you're exerting a force on it, why isn't it accelerating? Think about why it's not accelerating. And you can do that by identifying all the forces and draw a free body diagram. So go through and don't forget to compare the magnitudes of each of the forces. Hint, if acceleration is 0, what should my net force be? Also 0. So make sure as you're drawing the free body diagram that you go ahead and have a net force that is equal to 0. And we'll talk about this one in class. And that will actually conclude this part of free body diagrams, and we'll continue with Newton's third law in the next segment and close out this introduction chapter and then get into actual problem solving in chapter 5. All right, so we have one last section to go through in chapter 4, and that's getting back to Newton's laws. So we've already talked about Newton's first law. And Newton's first law is the law of inertia, where an object at rest tends to stay at rest and an object in motion tends to stay in motion unless an outside force acts upon it. Newton's second law, we came up with a formula that acceleration is the net force divided by its mass. So force causes an object to accelerate, and that acceleration is directly proportional to the mass. Inversely proportional to the mass and directly proportional to the force. And now we're going to get into the third law, which is commonly referred to as the action-reaction pair law. And we'll take a look at that right now. So I'll do a quick little demonstration in class, and I'm going to have two people with force plates. They're plates that can get pushed on, and they measure the force in newtons, and they are calibrated and zeroed out. They're going to push at each other, and one person is going to push onto the other one. And my question is, who experiences the greater force? So let's say that there's this big person here, and they got this force plate, and then there's like a little person here, and they got a force plate, and this big person is pushing and pushing and pushing, and let's say, for example, that they end up going to the right. And my question is, who experiences the greater force? And we intuitively want to say that this person experiences the greater force because they're moving to the right, they are being pushed around, they must be experiencing the greater force. And the reality is that's not the case. We'll see from the force versus time graphs that they actually experience identical forces. And it's a really, really weird concept and people always struggle with, because why would they experience the same force? And the answer comes into Newton's third law. So Newton's third law is that motion will often involve two or more objects interacting with each other. So for example, I have a hammer and it's driving down a nail, but we're saying that with that, there's this reaction pair of the nail resisting or exerting a force back on the hammer, and we're saying that they are the same. Same thing, if a bat hits a ball, your foot in a soccer ball, and the earth and the moon, there's all these action-reaction pairs. They involve two things happening or interacting with each other. Now, the interaction of objects
is it's the mutual influence that one object has on the other object. So right here we have A and B. They are B is pushing to the left on A. So B is exerting a force on A, but A is also exerting a resistive force on B. There's an action-reaction pair. An action-reaction pair, when dealing with forces, they exist as a pair or not at all. There has to be two forces. So there's this force of B on A, and then there's this resistive force of A on B. And that is what Newton's third law is getting after. So Newton's third law states that every force occurs as one member of an action-reaction pair of forces. So we're going back to the hammer on the nail. Then there's a force of the nail on the hammer, and there is a force of the hammer on the nail. Each force is a different object, but the members of the pair point in opposite directions but are equal magnitude, as we will see in our demonstration. So they're two different objects, but they're opposite directions but equal magnitude. It's a pair of forces. We actually see this in nature too, in that in order for you, for example, to walk, the floor needs to have friction. So you're pushing back on the floor, and the floor is pushing forward on you, and that's how you're able to go forward. The friction that actually is stopping us from slipping is static friction, and we've all been there when we're on ice or some other type of slick surface where the friction isn't high enough and we walk forward and we slip and fall. The static friction has to point in the forward direction to prevent your foot from slipping, because otherwise there would just be a net force to the right and nothing would counteract that. Same thing with a tire on a road. It also brings us into this concept of like rockets and that thrust force that we've been talking about a little bit in class. The rocket itself pushes hot gases off the back, so it has a force going down, but it allows the rocket to go up because of that action-reaction pair. So I got a quick check. A mosquito runs head-on to a truck, which is true about the collision. We like to say that the truck exerts more force than the mosquito because the mosquito is getting smushed. But the reality is the mosquito and the truck exert the same force as on each other. And when I think about that, going back to my concept that acceleration is F net divided by the mass, okay? The mosquito has a really, really small mass and therefore a really, really, really large acceleration. The truck has a really, really, really large mass and therefore a really, 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 really small acceleration. And that's why we can justify that the net force is, in fact, the same. A little follow-up question would be, what is the last thing that goes through a mosquito's head during a collision? And the answer, of course, is its butt. Yeah, so that will actually end our quick little introduction into Newton's third law, but we will have some additional conversation about it in chapter 5 and a couple of the applications behind it. So there is more that we can talk about, but that's just that quick little introduction. Forces occur as pairs. There's an action-reaction pair, or they don't occur at all.
Hi there, welcome back. So we spent a lot of time in chapter 4 building some background knowledge for what it is that we're talking about. We talked about forces. We gave an introduction into Newton's laws. We talked about free body diagrams. We did all this different stuff to set up stuff to get ready to solve it quantitatively. So that's exactly what we're going to do, is we're going to get quantitative with things. So part 2, this next part of our unit 2, is going to do just that. We're going to start taking a look at how we can solve these problems quantitatively, getting a little bit more of information in there and going from there. So the first part of this chapter, there is a pre-lecture video on static and dynamic equilibrium. And we'll talk about exactly what that means, but essentially this is going to lead us into how we quantify any problems dealing with Newton's first law. Okay, so we're going to start this by taking a look at our first pre-lecture video. And in this pre-lecture video, he introduces the concept of static and dynamic equilibrium. Equilibrium, of course, meaning balanced. So if I were to imagine a free body diagram, let's say of moving a box across the floor, I know that I have a weight force, a normal force, there's a force of a push, and let's say I'm pushing it across the floor at constant speed. That would give me some kinetic friction. And we've talked about this exact thing before, but this is in equilibrium because all of the forces are balanced. But the point in the pre-lecture video is there are 2 types of equilibrium. This example right here is dynamic equilibrium, meaning that it's in motion. The forces are balanced and the acceleration is 0. And as we know, any object in motion tends to stay in motion unless there's an outside force that acts upon it. So this one is in equilibrium and it's balanced at 0. But now what would happen if I just, instead of kinetic friction, let's say that I had static friction. Well, now the forces are balanced and the acceleration is still 0, but the object is not moving. And that brings us to the concept of static equilibrium. Static equilibrium means that the object is stationary. So we'll address both of these as they pertain to Newton's first law in this section. So our first section in chapter 5 is all about Newton's first law. So you just watch a pre-lecture video talking about static and dynamic equilibrium, and now we're going to get a little quantitative and look at some problems with them. So equilibrium, by definition, is anything that's balanced out. So in physics class, we will have an object that is at rest, in which case that means it's static equilibrium. So the forces are balanced out, but it's stationary. But we can also have an object moving in a straight line at a constant speed, and that'll be dynamic equilibrium. In both of these cases, there is no net force acting on an object, and the acceleration is 0, but that doesn't mean there are no forces acting on the object. It just means that the object is not accelerating, because as we've talked about over and over again, forces cause acceleration. So I do have a couple formulas for this. The sum of the forces in the x direction equals mass times acceleration. That's from Newton's second law, and that equals 0 because there is no acceleration. And the sum of the forces in the y direction, same thing, also equals 0. So this little weird looking E here, for those of you who aren't familiar with it, this is sigma. And sigma means the sum of all the forces. So the sum of all the forces equals the first force plus the second force plus the third force, etc. As we look in each direction, both the x direction and the y direction. We evaluate those independently of one another. So let's go ahead and jump right into an example problem. We have an orangutan weighing 500 newtons, hangs from a vertical rope. What's the tension in the rope? Well, if he's just hanging there, this is an equilibrium problem. So I can simplify it by drawing a free body diagram. I know that there's a weight force going down, and that weight force is equal to 500 newtons. And there's some tension force going up. Now, take a second and pause and just think about, if you can think about it
just with common sense, what is the value of this tension force? So pause the video, take a second to think about it. So many of you instantly thought, hey, that value's got to be 500 newtons. And that is correct. But obviously all of our problems aren't going to be this easy. So let's take a look at it, how we would set that up quantitatively. So we know that this is all happening in the y direction. So that means that the sum of the forces in the y direction equals mass times acceleration in the y direction, and that's going to equal 0. So when I mean the sum of the forces, I add up all the forces. And the sum of the forces, so there's forces in the positive direction, and that's going to be tension. And there's forces in the negative direction, and that's going to be weight. But in equilibrium, the acceleration is 0, therefore the sum of the forces is 0. And I can say that therefore the tension is equal and opposite to the weight. The tension is 500 newtons, so the weight must also be 500 newtons. I'm sorry, the weight is 500 newtons, so the tension must also be 500 newtons. So how I solve this problem is I said the sum of the forces in the y direction equals the mass times the acceleration in the y direction, and since it's in equilibrium, they equal 0. I added up all the forces in the y direction. The tension force, that is going in the positive direction, and the weight force, that is going in the negative direction, hence why I put that little negative sign there. I can also have multiple forces going in each direction, and I would add them all up, and we'll see that more later. Then I said that therefore that the two of them are in fact equal to each other, and therefore if my tension or if my weight is 500 newtons, then so must my tension. Here's just a quick little better picture or visual of the problem. And we know that the net force is 0 from that. So an orangutan is hanging, and we know the net force is 0. Here's, again, the free body diagram. And just like I did, we add up all the forces. You'll see that they did, in this example, there's a plus sign. That's true. The weight, again, is in the negative direction, so therefore I know that it is subtracted. And we can see that right here, they did a subtraction sign and said that that must be negative, but they're equal and opposite, so the tension has to be 500 newtons. So this is just a quick conceptual example. We said that the conceptual example is a rod is free to slide on frictionless sheet of ice. One end of the rod is lifted by the string. If the rod is at rest, which diagram shows the correct angle of the string? And this is a frictionless surface, which means that I can't rely on friction to counteract the forces. So the best way that I can evaluate this is by taking a quick look at the free body diagrams. So here are the free body diagrams. For scenario A, we look at, and it's right there. So we have a tension going off and to the left. We have a normal force from the surface going up. And of course, we have the weight force of the object going down. According to my free body diagram, I have a net force right there. And B, I have the weight force going down. I have a tension force going up and a normal force going up. And these two, those are actually all balance. So B is actually my correct answer. And C, same thing, tension going off to the side. That's going to cause me to have a net force going off to the right. So C can't be the right answer. So by looking at all of them, we want to look and see when the net force is 0. And that is when the tension is straight up and the weight is straight down. Another quick example for you. A car with a mass of 1,500 kilograms is being towed at a steady speed by a rope held at a 20-degree angle from the horizontal. So here's what I said before. These will start to get tricky because now we can start having forces being pulled at angles, and that'll make things a little bit more complex than we were used to, with just having straight in the x direction or straight in the y direction. But I solved the problem the same way, actually. So I'm going to start by drawing a picture of this object. And by me, I mean I'm going to use the picture that I already have. Hey, look, that was easy. So there's my picture of the object right on the left-hand side over here. And then on the right-hand side, I do have a free body diagram. And in that free body diagram, I see that this tension here, that's actually really important, is at that angle. So when I'm looking for the tension, I have to ask myself the question, what is tension? Well, tension is the force exerted on the rope. Where is that tension coming from? Some of you might ask that in your relationships. And the tension is counteracting friction, but the interesting thing is you're also pulling up on the car. So some of the tension is combining with the normal force to counter out the weight. This gets really confusing. Why is it confusing? Because this tension has an X component and a Y component. It's acting in both directions, hence that little that theta there, it's acting at an angle. Okay, so it's kind of weird, but I think I kind of got an idea, right? There's an X component of tension, and that's balancing out the friction force. There's a Y component of tension, and that's balancing out some of the weight in addition to the normal force. It's confusing. You have to be able to visualize the forces that are acting. And then I can say, all right, if it's going at a steady speed, which indeed it is, that means all of the forces must be balanced. So let me go ahead and go to the, say, well, we start with the sum of the forces in the X direction, that equals 0, and the sum of the forces in the Y direction also equals 0. So let's see what those statements look like on the next slide. So here is my sum of the forces in the Y direction, here is my sum of the forces in the X direction. And like I talked about before, in the Y direction, there's a normal force, there's a tension. There is no frictional force, but there is a weight force. And that all has to equal 0. In the X direction, looking at all the forces, there's a normal force. Oh, wait, nope, definitely not. No normal force in the X direction. There is tension, there is friction. Is there weight? No, there's no weight in the X direction. We're not on a hill. Okay, so I'm actually going through and taking a look at all of my forces and thinking what direction they act in. And when I do that, now I can actually go to that, and now I see the correct formula. So thinking about what forces are acting, that's going to help us solve this problem. But I know that each direction, they equal 0, so I can sub in and figure out exactly where my friction is. So here are my expressions for each direction. In the Y direction, I have the normal force going up, and I have a Y component of tension. Those are both positive, and then I have the weight force going down, that is negative. In the X direction, I have the X component of the weight, the X component of the tension to the right, and then friction to the left. Now, if I'm solving for tension, I can actually use either one of these formulas to figure it out. But since we were given this force of friction, I know that in the X direction then, T cosine theta, the tension, has to be equal and opposite to that 320 newtons. So I can use that to solve for the actual tension of this problem, and I'll do that right now. So the actual component of tension then is the force of friction divided by cosine theta. Friction was 320 newtons divided by the cosine of 20 degrees, and I get an actual tension of 340 newtons. Again, these problems can get very tricky, so I need to make sure I'm keeping track of all of my forces, and I do that with this nicely made free body diagram, and I know that the net force is 0. This is just one more little thinking about tension and how the tension is actually, like I said before, taking away from some of the normal force, because these two have to add together to equal out the weight. And one last little quick check. We have a ring as seen from above as being pulled by 3 forces. It's not moving. What's the force of this big F right here. That big F needs to cancel out each of these forces. And these forces are applied both in the X direction and in the Y direction. So therefore, I know that it has to cancel out definitely the Y direction, but these two actually right here, these X directions, cancel each other out. So really, all I care about is the Y component in each, which is going to be 10 sine theta. And if I cancel out both of them, I need to get a total force of 20 sine theta. So again, this is a very tricky section, and we'll be spending a lot of time practicing problems from this as we go through this chapter. So if you're overwhelmed, make sure you take a look at a couple of the problems, and we'll take a look at those in class. All right, so we just took a look at 5.1, which is taking a look at static and dynamic equilibrium and solving those problems. And in all of those cases, there is no net force, and therefore the acceleration is equal to 0. Now, we did look at some of the forces as mass times acceleration, but now we're going to look at Newton's second law. And in this case, in Newton's second law, when dealing with dynamics, we will have an acceleration. So an acceleration will not equal 0, and we'll have to solve problems based on that. Again, we'll look at free body diagrams, we'll look at the forces acting, and those will get us the acceleration through the net force. So with Newton's second law, Newtonian mechanics comes down to two main steps. First off, the forces acting on an object will determine its acceleration. Okay, the forces determine the acceleration, and we use the formula acceleration is the net force divided by the mass, and we can get that acceleration using the concept of forces, or we can use it with kinematics, and those two things help each other out. So with dynamics and Newton's second law, the sum of the forces equals mass times acceleration, and again, those are independent in each direction or each dimension, the X direction, the Y direction. Now with Newton's first law, we just set these equal to 0. Now we're saying acceleration is not 0, so they are not equal to 0. Okay, so let's go ahead and start with an example problem. And it says a golfer putts a 46-gram ball with a speed of 3 meters per second. Friction exerts a 0.020 Newton force opposing the ball, causing it to slow down. Assuming the direction is okay, will her putt reach the hole 10 meters away? All right, so again, we have a lot going on. And the question is asking me, I putt the ball, it's going some velocity, will it go some distance? So if I were to draw just a quick picture of this, the ball needs to make it into the hole, and that is 10 meters away. The ball is traveling at 3 meters per second, but it's undergoing some friction that's going to slow it down. So let me draw a free body diagram of this. And we know that there is a weight force on the ball. We know that there is a normal force on the ball. Those two are balanced, right? It's not accelerating up or down. So those are in equilibrium. However, because of friction is unopposed once she hits the ball. So this is our free body diagram, and we do in fact have a net force that is equal, or caused by, I should say, the force of kinetic friction. So there's two kind of parts to this. The part one is on the left. And with that, I want to use kinematics to figure out if she makes it into the hole. Part two on the right, I need to use dynamics to understand the net force, which gets us our acceleration, to plug in to our kinematics. Okay, so this picture is getting a little messy. So I'm going to go ahead and redraw it, and we'll pick up the video from there. Okay, so here is a better simplified version. I do have my free body diagram all the way over on the right, and that free body diagram shows me again the net force. Now, this can get a little confusing because the pictures have arrows going in different directions, but the ball leaves the putter and heads to the right. Acceleration is to the left because it is a negative acceleration. It is slowing the object down, and we see that in both pictures. So right here on the far left, this is my kinematics, and on the far right, this is my dynamics. And I need both to solve this particular problem. Okay, so I need to look at my formulas, and I know that the sum of the forces, and I did it quickly here, but the sum of the forces in the x direction equals all the forces acting in the x direction. Well, there is no normal force in the x direction. If I were to, again, I'm listing all of the forces, just like I did in the last unit. There is no normal force, there is no weight, and therefore, the only force I have acting in the x direction is the force of friction. Now, I also have the y direction, but with the y direction, this is an equilibrium. So I actually don't care about this at all because there is no motion happening really in the y direction. So I'm just going to get rid of that. And I'm left with that the negative force of kinetic friction or rolling friction, whatever you want to talk about, is equal to the mass times the acceleration. So if I solve for the acceleration, I can do that by plugging in the frictional force of negative 0.020 newtons and divided by the mass of 0.046 kilograms. And I get a acceleration then of negative 0.435 meters per second squared. From getting that acceleration now, I have this is part of my toolkit, and I need to figure out how far the ball actually goes. Now, there are a few different ways that I can go about solving this. You can see one of the ways right here. This is using the concept of VF squared equals VI squared over 2A delta X, and then solving for XF. The other thing I could do is I could say XF equals XI plus VI delta T plus 1/2 A delta T squared. And the problem with that is I don't know the time. So I could solve for the time that it would take to slow down to rest using VF equals VI plus A delta T. But now I'm getting all this extra work in, so I'm actually not going to use this. So this formula that is used right here, understand that it just came from VF squared equals VI squared plus 2A delta X. And all I did was I split up delta X into XF minus XI, and then I moved the XF over to the other side. So if I go ahead and plug in, the final velocity is 0 meters per second. The initial velocity is 3 meters per second, and that quantity is squared, divided by 2A, which is 2 times negative 0.435 meters per second squared. I get my final answer of a distance of 10.3 meters. So I know that the ball goes 10.3 meters. The hole is only 10 meters away. Therefore, I know that it's going to make it into the hole. And I can figure that out just by looking at the magnitude of the friction force and how much the object weighs. So we have a partner problem, which we'll take a look at tomorrow as with your partners. And it says a car with a mass of 1,500 kilograms is being towed by a rope held at a 20-degree angle. This problem sounds really, really familiar because we did it almost identical. But now we have a frictional force of 320 newtons opposes the car's motion. What is the tension in the rope if the car goes from rest to 12 meters per second in 10 seconds? Now, this is actually somewhat tricky because as we accelerate, the tension in the car is no longer equal and opposite to the force of kinetic friction. Or I should say the x component of tension, as we saw in the last problem. As we accelerate, we increase the tension in the cable. So the tension will actually be greater than it was in our previous example problem because of that acceleration. It causes the tension to be greater. So we'll take a look at that problem tomorrow in class. We will also have another partner problem tomorrow, and this deals with a sled of a mass of 20 kilograms, slides along a frictionless ice at 4.5 meters per second. And then it crosses through a rough patch of snow that exerts a frictional force of 12 newtons. So imagine you're going across ice because you were sledding across ice, and then you go off the ice into the snow. That snow is going to cause you to slow down. So we want to know how far does it slide before coming to a rest. So for these two problems, just take a couple minutes and set up a free body diagram, and that'll help us as we go into the problem tomorrow in class. You can also, if you want, even set up a pictorial representation that'll help us visualize the problem a lot better. And that is our introduction into solving Newton's laws. Now, for these problems, you saw that we got simple, really easy numbers like a frictional force of 12 newtons. So for the rest of chapter 5, we're going to dive a little bit more into each type of force, kind of figure out how we quantify each type of force, and then we'll continue to solve problems based on that. So right now, you're getting things like 12 newtons, okay? Super easy. But where does this come from? And this is this kinetic friction, for example. Then the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So we're going to get into understanding where these numbers come from and dive deeper into the quantitative examples that we can do. And we'll do that right away in the next segment.
All right, so now we have we've really done the bulk of the work of understanding how we set up and solve Newton's first law and Newton's second law problems, both the dynamic and the static and the no net force and all those different types of problems. And we did that one in the last two sections. And now in the rest of this chapter, really, what we're going to be doing is taking a look at some of these forces that we already introduced and going a little bit more in depth. To understand them a little bit better. And the way we're going to start is we're going to take a look at weight and apparent weight. So we know we all have weight. We'll talk about a formula for that, but we also have an apparent weight, and we'll get to talk a lot about that as well, both in this chapter and in the next. So this pre-lecture video, it's about a 7-minute long video where he's taking a look at the concept of weight and apparent weight. And one of the best ways you can do that is by going into an elevator. And in an elevator, depending on the direction you're moving and whether you're speeding up or slowing down, your apparent weight actually changes. And you know that this is true because if you go into an elevator, you get these weird feelings when you're riding up or riding down the elevator. So sometimes you feel like you're getting scrunched together. Sometimes you feel weightless or light, like you're floating in the air. And that's due to the net force of caused by the acceleration, and that is what changes your apparent weight. So in the pre-lecture video, he goes into great detail about this, and it's a good video to watch to take a look at that. Okay, so the first little section we're going to talk about is the difference between mass and weight. We'll talk more about apparent weight in chapter 6 as well, and right now, but we're focusing on the concept of mass and weight. So mass and weight, although commonly interchangeable in the physics realm, are really not the same thing. So mass, when you first learn about mass, probably in elementary school or middle school, mass is how much stuff makes up an object. Now, in physics, we go a little bit different, and we say it's a quantity that describes an object's inertia. And the reason is it doesn't matter where you are, you always have the same mass. You could be in the middle of space and you'll have the same mass. Weight, however, weight is a gravitational force. It's the force of gravity, and we've talked about that. We said that weight is equal, or can be also described as the force of gravity. And we'll talk more about the gravitational force in chapter 6 as well. But for right now, we're just saying our formula for weight is mass times gravity. And you see that I have that little negative sign there, and that's because the weight force is always straight down to the center of the Earth. And the weight in this case is the only force acting, so the net force is the weight. This would be an object that's in free fall. So when we're going in between weight and mass, the really easy version is for us to just say mass times gravity and just add a 0 at the end of the mass, because we just say gravity is 10 meters per second squared. It makes it really easier. This is just a really a basic table of conversion factors going in between mass, weight, and force, and not something that we'll spend really any time with, because we just use the metric system anyway. So let's start off with a quick little example, and that is what are the weights in newtons and the masses in kilograms of a 90-pound gymnast, a 150-pound professor, and a 240-pound baseball player. And I'm sorry, football player. So in this case, we're just looking at doing conversions. So I'll just set up the first one. So if we're looking for the weight of the gymnast, well, it's 90 pounds. And if we're converting into newtons, 1 pound is 4.45 newtons from that conversion factor. Again, I'm not going to make you do this really ever, and that's 400 newtons. That's her weight in newtons. The mass, I would do the same thing, except now it's 90 pounds, and 1 pound is 0.0454 kilograms, otherwise known as, the way that I always learned it was 1 kilogram is 2.2 pounds, but either way, 41 kilograms right here. So kind of just a quick little video, or a quick little reminder in unit conversions, not something that's going to be super important in this unit. And here are all of the answers for those objects as well, so if you need to quick go through them, you can pause the video here. So now that we know what mass and weight are, let's talk about apparent weight. Now, apparent weight is, in physics, it's the weight of an object. Well, the weight is the force of gravity on the object, but apparent weight is your sensation of it. How do you feel in that situation? Your weight does not change, but your apparent weight, it absolutely changes. And our definition in physics is the magnitude of the supporting forces, supporting contact forces. And really what that equates down to is it's your normal force. And your normal force can actually change based on your acceleration. So we'll take a look at that again throughout this chapter, as well as chapter 6, which is all about circular motion. You think about being in a car and going over a hill, and you feel this lightness, this weightlessness. That is because your apparent weight is changing. So when you're in an elevator, there's a few different forces acting, right? We have just the normal force and the weight. That's it. That's the only forces acting on you. And the normal force, whenever you're, in this example, you're going up, right? So your acceleration is up, so your net force is up. So your normal force has to be larger than your weight. So the normal force then is the weight, because it counteracts that going down, plus your mass times acceleration, which is the net force. So this concept right here, this is F net. So the net force plus your weight is your normal force, and that is your apparent weight in this case. So this feeling that you get when you're in the elevator is your net force, or I'm sorry, your apparent weight. Now, when I think about this, when I first go in an elevator and I push the button to go to the top floor, I feel like I'm being compressed, or I feel heavier. And the reason that I feel heavier is because I have a larger apparent weight as I go up the elevator. Why this happens? Well, Newton's first law says an object at rest tends to stay at rest. So your inertia actually wants you to stay at rest, but the elevator pulls you up, and you have this resistive force, and that makes you feel heavy. Conversely to that is when you're at the top of the elevator going down, or you're going up, slowing down. There's a few different things, but when the elevator comes to rest, my body wants to stay in motion. So as the elevator slows down, as I'm going up, I feel weightless, or I feel light. Okay, so we're going to do another example problem. We have somebody is standing on an elevator that's moving at 5 meters per second. So we know it's moving. And it says Anjay's mass is 70 kilograms. So we know regularly his weight is 700 newtons. So this 70 kilograms right here, his actual weight then is 700 newtons. We just add that zero. But as the elevator stops, it reads 750 newtons. Okay, so that means he feels heavier than what he normally does. So in this case, if he's already moving and he feels heavier, that means that I need what we just talked about, our apparent weight, is going to equal the regular weight plus mass times acceleration. This means that this acceleration needs to be positive. So if I'm going up at 5 meters per second and then slowing down, because we know it's slowing down because as the elevator stops, then that would mean that I would feel lighter. So what actually is, I'm going down the elevator, and as the elevator slows down, I get this greater apparent weight. So that answers half the question, but it also asks, how long did the elevator take to come to rest? Well, for that, we're going to need the acceleration so we can solve for that. So let's go ahead and do that. And if I look here, the acceleration then is going to equal the apparent weight minus the regular weight divided by the mass, which is 750 newtons minus 700 newtons divided by 70 kilograms. And I get 50 newtons divided by 70 kilograms. And I get an acceleration of 0.71 meters per second squared. So with that acceleration, I can go back into kinematics. I have VI is 5 meters per second. VF is going to be 0 meters per second. And then my A is 0.71 seconds. And I can use kinematics to solve for that. And I will let you go ahead and do that or check out a later slide. But we get about 5.5 seconds. So here is, again, the work to set up the math for the acceleration. You can see that in this example, however, they did use the 9.8. So that's why we get a slightly different acceleration. And using the kinematics, VF equals VI plus AT, we get a time that it takes of 5.5 seconds to come to rest. So this concept of weightlessness then is a great application. And if you haven't ever seen this before, this is known as this plane right here. It's a NASA plane. It's known as the vomit comet. And the reason is well, people tend to throw up. They must be teaching physics up there. But a person, when they're in free fall, so this vomit comet, they go up really, really, really high, and then they nosedive so that the people inside feel like they're in free fall, like they're skydiving essentially, but they do it in such a way that they're floating around inside the plane. And the reason that they do that is that it simulates a zero gravity situation. Now, that's not actually a good terminology, zero gravity. An object that is in free fall appears weightless, not because it doesn't have weight. There is still a gravitational force that's pulling it down. The reason it feels weightless is because there's no apparent weight. There's no normal force. You have to have a normal force to feel like you have weight. So that it's a thick concept in physics, but an object that is weightless has no apparent weight. It still has weight. Gravity is still pulling it down, but it appears weightless because there's no supporting forces. This is actually Matt Herr. He's a instructor at Platteville. He got to go on the Vomit Comet, and he got to test his GoPro camera stabilization system. So he made his own GoPro camera thing that holds a GoPro but stabilizes around him as you're in free fall in space. So pretty cool. He's a high school physics teacher out in Platteville, but he got to ride the Vomit Comet to test out some stuff. All right, so we're gonna follow up with a quick check. It says a 50 kilogram student gets in a 1,000 kilogram elevator. Hey, spoiler alert, that whole 1,000 kilograms, we don't care how much the elevator weighs. It rests and stands on a metric bathroom scale as the elevator accelerates upward. So as he goes up, he's accelerating up. He has positive acceleration. Therefore, his apparent weight will be greater than 490 newtons. Okay, next one. Now, same thing, and sadly, it says the elevator cable breaks. What is the reading on the scale during the few seconds it takes the student to plunge to his doom? Well, in this case, we're again in free fall. So if he's in free fall, there is no apparent weight because there's no supporting contact forces, and he has a 0 Newton apparent weight. He feels weightless. He's in free fall. So there's an extension, and occasionally it pops up on the AP exam, but it's inertial mass versus gravitational mass. Now, your mass never changes. Your weight changes depending on the planet that you're on because it's a gravitational force. The concept of mass, however, does not change. But how we get it or how we solve for the mass can change. So inertial mass versus gravitational mass. And essentially all this means, if we take a look at our AP equation sheet, anytime that we have mass in a problem or in a formula, such as looking at the weight, right? So if I know the scale reading of an object, like a spring scale or a scale that I'm standing on, then a spring scale pulling down, then I know that this is a type of gravitational mass because it depends on free fall acceleration. However, if I'm in space and I am stretching a spring out, which we'll talk more about later, and I let it oscillate back and forth, which we'll talk about more later, that actually does not change from planet to planet. So that's what we refer to as its inertial mass because it never changes. The inertial mass doesn't rely on gravity to solve for it. So gravitational mass uses G. Inertial mass does not use G. So it's just a quick little extension. We may or may not see a problem like that throughout the year or sometime during the year. But just a heads up, when we talk about mass, that's something we're talking about. All right, so that's actually it for your introduction into mass and weight. We will continue in the next section to continue to break down forces and in the normal force, and we'll do that in the next section. All right, so the next section the next topic we're gonna address a little bit more is about the normal force, and we've talked about the normal force a little bit. We said that it's anytime you have a surface pushing back, so let's talk a little bit more about that. So what we've talked about is we've said that an object at rest on a table, we know that there's an upward force from the table, right? We have the weight going down, and therefore we have the normal force going back up. And we've said this before, it's called the normal force because it's always directed normal or perpendicular to the surface. So we've talked a little bit about pushing against a wall too, and that's also an example of the normal force. But the normal force, it can kind of vary. What we like to say, it adjusts itself so that the object stays on the surface without penetrating it. So whatever forces are going down, the normal force has to be equal and opposite to the force that it's matching. So this is caused by bonds at the molecular level. The harder you push on the table, they want to keep that equilibrium, so they push back a little harder. So let's do a quick little example. If we have a 1.2 kilogram book lies on a table, the book is pressed down with a force of 15 newtons. What's the normal force? So if I were to draw a free body diagram here, I know that there is a weight force going down that's equal to 12 newtons, and there is a extra force of a push, just a general force F, and that's pushed down with 15 newtons. Notice how both of my forces are drawn from my free body diagram. I just made my particle a little larger. Well, if that's the case, then I got 12 newtons going down and 15 newtons going down, which means that my normal force is going to be equal to 15 plus 12, which will be 27 newtons. So pretty simple concept. It's equal and opposite to whatever that force is. And here's just a visual of that. We also know that and see that the net force is equal to 0 because it's in equilibrium. Okay, but anytime that we're not on a flat surface, we could be on, for example, a inclined surface. Anytime when we're analyzing forces on an incline, the normal force still has to point perpendicular from the surface. So what we won't do, though, is we won't change the way that the weight force is. The weight force is still straight down, right? There's always weight going straight down towards the center of the Earth. So when we draw this, we're actually going to rotate our x-axis to match the surface. So this becomes our positive x-axis, and this becomes our y-axis. And we do that so it's a little easier to break down the components to talk about them. So the weight force is still going to point straight down. The normal force is going to point perpendicular to the surface, and the angle that we tilt it right here is going to match the angle that our weight force is changing right there. And that is also having to do with complementary angles or something like that from geometry. So a couple common mistakes to avoid. The normal force is not straight up, right? It is perpendicular to the surface, and the weight is not straight in the y direction. It is straight down. So here's a quick check for us real quick. It says a box is sitting on the floor, accelerating upwards. The elevator is accelerating upwards. How does the magnitude of the normal force compare? Well, if it's accelerating up, that means there's a net force up, which means that the normal force has to be larger than the weight, because the weight's the only force down. If there's a net force up, then the normal force has to be larger. And when you're in an elevator, this is when you feel like you're heavier. Now we have a box that's being pulled to the right at a steady speed by a rope that angles upward. So in this case, if I were to draw my free body diagram real quick, I do have a weight force, and we've actually talked about this before with the car being towed. I have this tension force going up and to the right, which means that there is an x component of the tension force, and that helps to take away or helps to balance out the weight. So the normal force itself is actually smaller than the weight. And then, of course, if it's towed at a steady speed, then I do have a force of kinetic friction also going to the left. But in this case, the normal force has to be less than the weight because there's that tension in the x direction that's helping, or sorry, tension in the y direction that's helping pull it up so that it experiences less normal force. And I talked about this in class where if I'm pulling something, if I pull up on it, it actually makes it easier to pull because we're decreasing friction by decreasing the normal force. And we'll talk more about friction later. All right, so we got another example problem. A skier slides down a steep 27-degree slope. On a slope this steep, friction is much smaller than other forces at work and can be ignored. So there is no friction. What is the skier's acceleration? All right, so let me sketch this out real quick. That's not a great 27 degrees, but what the heck. All right, 27-degree slope. The person's going down it. So let's think about the forces that are at work. So remember that I am going to tilt my axis so that it goes with the incline. So there is a normal force, obviously, that's going straight up. There is a weight force that's going straight down. I'm sorry, the normal force straight perpendicular to the surface. The weight force is going to go straight down. So let's get a better visual of that. Well, we know that if it's larger, if the friction force is ignored, we know that the skier will accelerate down the hill. And what is causing that acceleration? Well, if I look, there is an unmatched component of the weight. The weight in the x direction is equal to the acceleration of the object. I'm sorry, is equal to the net force, which is equal to mass times the acceleration of the object. So let me clean this up a little bit with a nicer picture. All right, so here's a little bit more of a cleaned up version of this picture. You can see that I have the normal force going straight perpendicular, and I have the weight going straight down. And the net force off to the side here is caused by, as we talked about in the last slide, is caused by the weight in the x direction. So if I'm looking at my picture, or if I'm looking at the math behind it, however you want to call it, there is a normal force, and that's balanced by the weight in the y direction, and then the weight in the x direction is what's causing that acceleration. And probably not the best drawn here, but this is my right angle right here. That's my weight, and we said that this angle right here is equal and opposite to this angle over here. So in here I have my right angle, I have the actual angle right here, and the x component is opposite of the so the x component is opposite. So anytime we use opposite, we're going to of course use sine. So my net force is going to be equal to mass times acceleration, and in this case it's going to be weight, the weight force, times the sine of theta. Well, that equals mg sine theta. It's the x component of the weight. So let me go up all the way up top here. So that means I'm saying that ma is mg sine theta. Okay, I have mass on both sides, so I can cancel that out, and I get a equals g sine theta. And if I think back, this would be acceleration in the x direction. If I think back, that is exactly what we talked about in kinematics when we talked about motion on a ramp. This formula is exactly the same as it was before. And that completely makes sense because just because we're analyzing a different way of looking at a problem, it doesn't change the acceleration of the problem. The physics doesn't change because of how we're looking at it. The physics has to stay the same. So I'm going to go ahead and running out of room. So the acceleration in the x direction equals 10 meters per second squared times the sine of 27 degrees, which when I plug that in my calculator, that'll get me right around 4.54 meters per second squared. All right, so we've taken a look at the weight and the normal force. We are going to do a lab real quick next on the Atwood machine, or the modified Atwood machine, which is something that we looked at when we first looked at Newton's laws and what forces cause. We do have some more practice problems that we're going to do, but now the next thing we're going to do is we're going to jump more into friction and take a look at what the difference between static and kinetic and rolling friction are. And then we're also going to take a look at air friction, or drag, as better stated. And those two we'll take a look at in the next segments.
Okay, so as we continue to build our understanding and catalog of forces, we're going to dive back a little bit and talk a lot more in depth about friction. And friction is it's a very relevant force in all aspects of life, because friction is something that typically can't ever be ignored. It always opposes motion. It's always slowing things down. It's the main reason why things come to rest. So we're going to take a look
more in-depth look about friction right now. So in this pre-lecture video, he talks about the different types of friction, but the main thing is actually popping up right now. The main thing that you need to remember is that friction always opposes motion. It's always in the opposite direction. So if I'm moving to the right, then friction is acting to the left. Now we're going to dissect each type of friction a little bit more in depth, but he goes through and talks a lot about the difference between static friction and the difference between kinetic friction, and how these two are very similar yet very different. And the main things to remember is that static friction is stationary. Don't know why I did it like this. And kinetic friction is in motion. Okay, so we'll talk a little bit more about these in this segment. All right, so now in 5.5, we're going to talk about friction. There's three types. We have static friction, we have kinetic friction, and we have a brief introduction into rolling friction. Now, all of these have the same general formula, but we'll talk a little bit more about each type in this segment. So in class, I'm gonna do a little demo, and I'm gonna use a force sensor to measure how much force is needed to pull a cart. And I have a few different extensions of this. I start to pull a cart, to start pulling it, and then how much is actually pulling it. Then I change the cart to on its side. Then I pull a different type of a cart, and I'll talk about that. And then I pull a heavier cart. And so I'm going to do this in class, but I also want to take a brief minute just to talk about the different graphs that we get. So the real, or the first one, I guess you could say, is the red line. And the red line, it might be a little hard to see, but it's on the bottom right here. And this is just 3 masses on a felt cart, and the felt is on the lab surface, the lab station, and then I pull it across. And when I look into all of these graphs, they all have this general trend. And I can see it best probably in the purple one because it's the biggest, but I start pulling, and I start pulling, and I peak, and then I drop down. And this is the concept of what is the difference between static friction and kinetic friction. So when an object is at rest, it's under, and you start to pull on it, it's static friction. But eventually, you have to break that static friction to get it in motion. So we see that general trend. But now I'm going to look at a couple other things. Now I have this blue line, and the blue line is 3 masses, still 3 masses on the side of a cart. And we notice that for the most part that these are actually identical. So friction is not a function of the cross-sectional area that you have it with. And it's kind of a weird concept, but if I have less area, there's less in contact, but there's also more force acting in that smaller area. So I'll talk about that a little bit more later. But then we got this green line, and this green line represents 3 masses on a cork cart. So the difference between, if I could imagine like cork versus felt, felt's a lot smoother, so there's a lot less friction. But then also I have this orange line, and this orange line is even a little higher than that, and the orange line is 6 masses on a felt cart. So if I have more mass, I also undergo more friction. And that kind of makes sense too, right? Because I'm pushing down on the surface harder. And then finally, I have, in purple, I have 6 masses on a cork cart. So we see that as the highest amount of force needed to get this thing in motion, because it's got the most amount of mass and it's got like the roughest surface. So we'll see that in class, and hopefully we'll be able to build some connections with that. So the first type of friction that we're going to talk about is static friction. And here, as we talked about before, here is somebody that is pushing on this box. So this girl is exerting a force. There's definitely a force being exerted, but the box isn't moving. So whatever she pushes forward with, static friction is pushing back with. So static friction is the force that a surface exerts on an object to keep it from slipping across the surface. If I imagine putting something on an incline, right, gravity's pulling it down. If it's not moving, static friction is keeping it up. if we ever need to find the direction of the static frictional force, we kind of go in the direction that the object would move and make it the opposite. So the static frictional force will go in the opposite direction. So it always opposes the applied force. So in this example, this person's pushing on the box. The box is pushing back because of friction. There's a frictional force from the surface that's pushing back. So this is in static equilibrium. The box isn't moving and it's not accelerating. So the static friction force, therefore, has to be equal and opposite to the force of the push. The question is, what if she pushed less hard? Well, then her force of the push would be a little less. But if we're still in static equilibrium, then the static force must also be a little less. So that gets a little confusing because now I just said I changed the magnitude of the force. So let's take a look at what those free body diagrams would look like. So in the first example, A over here, we have a person pushing gently, and we see that the forces are balanced. If the person is pushing harder but still not moving, the force grows, and so does the force of static friction. And then eventually I'll get to a point where I can push the maximum amount that static friction can withhold. And if I look back with the first graphs that I have, that's what this graph looked like. It was this, and then it came down. We're talking about this maximum amount, and that is this maximum amount of static friction. So static friction, the harder and harder you push, the harder the friction pushes back until you reach its maximum possible magnitude. And that equals, there's a formula for that. It's mu s times the normal force. Where mu s, so this is the Greek letter mu, it's called the coefficient of static friction. And that depends on the surface. And we're going to do a lab about that on tomorrow, essentially. So the direction of the static friction always opposes motion. The magnitude has to adjust itself so that the force is zero, the net force is zero. So the force of static friction can increase and increase and increase until it reaches its maximum value. If it's greater than that maximum value, the object will slip and start to move, and then that leads us to the concept of kinetic friction. So static friction, a very, very difficult to understand concept for people that are new to friction, but and it's a little frustrating, but we just got to remember that the static frictional force changes based on how hard you push until the object starts to move. And once it does start moving, we do get into kinetic friction. And kinetic friction is much, much, much easier. Kinetic friction has a constant magnitude that's equal to the coefficient of kinetic friction times the normal force. So in this case, this woman is pushing the box. There's a push exerted. The force of kinetic friction is opposite of it. The net force is zero. We're going at a constant velocity. I can also, I demonstrated this in class, I can also push the box fast. And my free body diagram is actually identically the same. Remember, forces don't talk about velocity. Forces never talk about velocity. Net forces have or go to acceleration, not velocity. I don't know why I did that. There's velocity. Here's a red line, not velocity. So even though in this case she's pushing faster, the net force is still zero because the forces are still balanced. So there's also this concept of rolling friction, and this is a very difficult kind of thing to think about, but it makes sense. When a wheel is rolling on a surface, there has to be some type of friction. The wheel is pivoting around a point. Kinetic friction has to deal with the sliding of something across a surface. So that's actually not a good representation. There is a small part of the wheel that is contacted to the surface that is stationary with respect to the surface, so it's not sliding. So instead, we call this the interaction between a rolling wheel and the road. We call it its own type of friction called rolling friction. This will pop up extremely little in this class.
It's just a different way of thinking about it. We worry just mainly about kinetic and static, but there is a small little extension known as rolling friction. Okay, so in each of these examples, we saw this mu with a subscript, and those are right here. These are coefficients of friction. And all that means is that if I have a surface and another surface, how they interact with each other is actually constant. So for example, if I have rubber on concrete, the coefficient of friction for static friction is 1, and for kinetic friction is 0.8. You will see 100% of the time that static friction, the coefficient of static friction, is larger than the coefficient of rolling friction, or I'm sorry, kinetic friction, because it takes extra force to get something in motion, but an object in motion tends to stay in motion. So once you get it in motion, then we get into kinetic friction, and these coefficients are always less than the previous example. Always, 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 always. And again, that goes back to that graph where I had like a peak and then it drops down. This is F static max, and I can solve that with these coefficients of friction. These are not anything that you will ever have to memorize. You will always be given them, or technically you can also solve for them if you have other information. But those are coefficients of friction. In our lab tomorrow, we'll deal with taking a look at different types of coefficients of friction for different surfaces. So to give you a quick little summary here, these are the formulas for each of the frictions. Now the easy ones, kinetic, kinetic, we have the coefficient of kinetic friction times the normal force, and it opposes the motion. Rolling friction, exactly the same. The complicated one, and this is where people struggle, is static friction. Static friction has some magnitude that is equal and opposite to the force that's being applied, which is less than or equal to its maximum static frictional force, which is equal to the coefficient of static friction times the normal force. And again, this one's complicated. I can push harder and harder and harder, which means that the force opposing my motion gets larger and larger and larger until I reach this maximum static friction, and then I break it and go into kinetic friction. But the maximum static friction is the coefficient of static friction times the normal force. Again, it's complicated. It's a weird thing to wrap your head around, but it's true, because there has to be no net force if there's no acceleration. All right, so let's jump into a quick little example problem here. And we have, does it move? So we have a box with a weight of 100 newtons is at rest. It's then pulled by a 30 Newton horizontal force. The coefficients of friction are labeled on the diagram. I have static friction and I have kinetic friction. And I want to know, does the box move? Well, if I need the box to move, then I need to break static friction. So really my question is this greater than or equal to F static max? I'm not sure that I put the equal sign. Yeah, I put the equal sign in the right spot. Okay, awesome. So in order to break static friction, then the force applied has to be greater than F static max. So the force of static friction max is the coefficient of static friction times the normal force. The coefficient of static friction is 0.4 what? Well, oddly enough, a coefficient just relates to the surfaces that are in contact. So anytime we have a coefficient, it's actually dimensionless, aka unitless. And the normal force in this case, we're on a nice flat surface, so that's just going to be equal and opposite to the weight, which is mass times gravity. So the mass is 100, oh, well, actually, we can just leave that as newtons, right? It's already in 100 newtons. So that means that it's 40 newtons. So the maximum static frictional force can exert up to 40 newtons. I'm only pulling at 30 newtons,
So my answer is no, the box does not move. And it doesn't move because it doesn't break static friction. Now, a follow-up question was, what if the box was already in motion? Well, similarly, this coefficient of kinetic friction here is 0.2, which means that the force of kinetic friction is 20 newtons. So if the box was already moving, because there's 30 newtons over here and only 20 newtons over here, it would continue to move and actually start accelerating because the force is greater than, the force applied is greater than the force of static friction. I'm sorry, kinetic friction. All right, so we got a partner problem that we will, of course, do in class. But this gets into this concept of you've probably seen them maybe advertised before, but furniture sliders or sofa sliders. So Carol's got this 32 kilogram sofa, and she wants to move it. So she used these sofa sliders with a coefficient of kinetic friction of 0.080. Again, no unit, on the carpet, under the feet of the sofa. She then pushes it at a constant 0.4 meters per second across the floor. How much force does she apply to the sofa? So we'll take a look at this example problem in class, but we're just essentially, if she's pushing it at a steady speed, right? That's what it says, a steady speed. That means that this is an equilibrium problem. But if it's in motion, it is a dynamic equilibrium problem, and it'll stay in motion. And we'll take a look at that in class. If you want to take a look at the free body diagram that I just talked about, it's this guy right here. But like I said, we'll take a look at it in class. So one last little concept is what actually causes friction. And friction, you think if you have things like ice on ice, you think that friction is essentially zero. And it does. It does get really close to zero because ice is a very smooth surface. But all surfaces at a microscopic scale are actually very rough because of the random molecules and alignment of that. They're actually very rough. So when two objects are placed in contact, if I look at my picture here, there are some points that jam against each other, and that causes resistance. So friction is just that. It's the resistance that two surfaces have with each other. So actually, ironically, these are Mizuno shoes right here. And Mizuno, if you're interested, Mizuno, Mizuno makes probably the best in the business for volleyball shoes. And when you think about being on a gym floor, your surfaces are going to be a little bit flatter and you slide around a little bit. So when you get good athletic shoes like Mizuno shoes, they have extremely high coefficients of friction because of the design on the bottom of them, and that allows you to get much better traction. And then with better traction, you can get greater acceleration. So people need and have to have good shoes when they play sports like basketball and volleyball because it gives them good traction because of the rough context between the surface and the shoe. All right, so we got a quick check here. Box is being pulled to the right. The tension force is greater than kinetic friction, so the box is speeding up. But then suddenly, the rope breaks. What happens to the box? Well, we know that there's still friction opposing the box, kinetic friction. Once I get rid of the tension, the only force acting in the X direction is friction, and it's acting opposing motion. That will cause the box to slow down and then eventually stop. Okay, so it doesn't keep its speed for a while. It's gonna, as soon as I lose that tension force, it's done accelerating. It's done getting that force driving it to the right. So it's instantly gonna start slowing down. It won't stop immediately because it will take time to accelerate. Now, if you have a really high coefficient of friction, that'll lead to a really high acceleration, but it doesn't stop instantly. All right, so we got another partner problem that we'll take a look at during class. This one is actually pretty complex, and I love solving it because of how complex it is. And it really brings together kinematics and dynamics. But we have a car is traveling at 20 meters per second, and it stops at a distance of 50 meters. Can I do anything with that? Yeah, you bet. I can find the acceleration, right? Assume that the acceleration is constant.
The coefficients of the friction between the passenger and the seat are 0.5 and 0.03. And my question is, will a 70-kilogram passenger slide off the seat if not wearing a seatbelt? So this is actually a really important concept. Why do we wear a seatbelt? If we have a drastic change in acceleration, I need something that's going to keep my body in the car. And we've all seen videos or pictures or whatever of people that haven't been wearing their seatbelts and are involved in high-speed collisions. And if they don't wear them, you can get launched through the windshield. And the reason is an object in motion tends to stay in motion. So you being in the car, if the car is traveling 20 meters per second, you are traveling 20 meters per second. Okay. That being said, you're sitting on a seat, and that seat also has a little bit, not much, but a little bit of prevention for you sliding forward. So actually, it says here the coefficient of kinetic friction. I don't need that. Okay. I'm just curious at, given this acceleration, whatever this acceleration is the force that's causing that acceleration greater than the force of static friction? And if it is, then I will slide off my seat. If it's not, then actually I'm safe. Now, I'm not telling you to not go home and put your seatbelt on. I'm just saying that there is a limit to this acceleration, and if you're under that limit, if your acceleration is small enough, then static friction by itself is enough to prevent you from moving. And if I think about that, that kind of makes sense. I'm trying to think of some real life examples where, like, let's say you're on a sled, right? When a sled's moving to a stop, you don't instantly slide off the sled. But if your sled hit a tree, you might go flying forward, okay? That's all I'm trying to say. So we'll take a look at that problem in class. Hey there, welcome back. We just finished talking about friction, and friction is something that opposes motion. And now we're going to look at something very similar, something I like to call air friction, known as drag. So drag is essentially the air equivalent of friction, and we're going to take that apart a little bit today. Now, at the beginning of the year, when I first talked about free fall, I said all objects in free fall, regardless of their mass, accelerate at the same rate. And that's a very difficult thing to back up in real life. If I imagine dropping a bowling ball and a feather at the same time, then the bowling ball is obviously going to hit the ground a lot quicker. But we said that that only applies to objects that are in a vacuum. And now we're going to briefly just take a little bit of look at drag and see how that plays and helps us understand why that happens in real life. So drag, the drag force, it is a force, and exactly like friction, it's always opposite in direction to the velocity. So it's something that opposes motion. So if I'm traveling to the right, then drag is opposing that motion to the left. And an interesting thing is that it increases in magnitude as the speed increases. So it increases as the speed increases. And I'll address that a little bit more in just a second, but we also see that at relatively low speeds, which is a vast majority of what we do, the drag force is really small and it can be ignored, but as speed increases, so does the drag force, so it becomes more important. And the way, my quick little introduction into this, and we'll talk more about it, but if you think about air is a fluid. Water's a fluid too, but air is a fluid just as much as water is. It's just a different type of fluid. So if I imagine that in air, there are all these like dots, all these air, this is really not going the way I thought it would. There's all these air molecules. And as I travel, or I traverse the medium, if I want to walk, I have to push all these air molecules out of the way. And the faster that I walk, the more air molecules I encounter, so the more that I have to push them out of the way. Okay? Just like if I'm swimming, the faster I swim, the more water I have to push aside. So these things kind of make sense, is that it's literally me pushing air out of the way. And we've all
experienced it to some extent where if we're running into the wind versus running with the wind, right? There's all these air molecules, and they can help us or hurt us depending on what we're doing. So the drag force does have a very nice formula, but it's a little tricky. So the drag force, there's this half thing, there's this drag coefficient. And we had coefficient before when we talked about friction, but it's the drag coefficient exactly the same as the coefficient of friction, where it just kind of depends on what the object is. Then we have this factor of rho. And rho is density. From physical science or from other science classes, you know that rho is density, which is mass over volume. In chemistry, you might just have it called D for density, but it's actually rho. And so the thicker the fluid, the more drag you encounter. And that makes sense, right? Because if I'm running through air versus running through water, it's a lot easier when I have a lower dense fluid. A is the next thing. A is the cross-sectional area of the object. So if I think about like a parachute, a very, very wide parachute is going to experience more drag than a narrow parachute. And that makes sense because if I'm like in a military style parachute, I'm going to have a lower cross-sectional area so that I can go faster. So I encounter less drag. And then finally, the last little part is the velocity. So v is the velocity of the object. So I can see that as velocity increases, the drag force that I experience will also increase. So the faster and faster I go, the more drag I experience because I'm pushing more and more molecules out of the way. Now, the problem with this is that we know that forces cause acceleration. So if I increase the velocity, I increase the drag force, and I increase the magnitude of the acceleration. In this case, it's actually this is going to be a negative force. It's going to take away from gravity or something. But if that gets me a new velocity, which gets me a new drag force, which gets me a new acceleration, which gets me a new velocity, which gets me a new drag. Okay, so the problem here is that by having the drag force, it makes things a little complicated. And the only thing that we can really do is take a look at a quick application of it, because the only way that we can correctly solve this mathematically is with differential equations. Unfortunately, Calc 3 is where you really get into differential equations, so we can't do a ton of it right now. But we can still talk about it, and we can take a little look at it without getting too deep into the math. So one of the easiest applications of drag is this concept of terminal speed. Terminal speed is just an application of Newton's first law. We have an object, in this case it's like a basketball, and it's flying through the air. Now there's a weight force that's pulling it down. It's accelerating down. When it first starts accelerating down, it's accelerating at free fall. And then there's a drag force that's opposing that motion. Now, as it gets faster and faster, it encompasses more and more drag. So the faster it falls, the further it's going to fall, and the drag force will increase. And it'll keep increasing, causing the acceleration, so that as the drag force increases, the acceleration will actually decrease, until eventually we reach what we call terminal speed. And at terminal speed, the drag force is equal and opposite to the weight. So that means then that our net force is equal to 0. There is no net force, there is no acceleration, and we're falling at some constant velocity with no acceleration. Acceleration equals 0. So the weight force is causing the object to fall, and then eventually it's falling fast enough that the drag force is causing an opposite force in the opposite direction, and we call that terminal speed. So if we're looking quantitatively at terminal speed, we can solve for velocity. We know that in this case that the drag equals the weight. The drag force is 1/2 times the drag coefficient times rho times the cross-sectional area times the velocity squared. And the weight force is mass times gravity.
So if we solve for V is going to equal the square root of 2mg over C rho A. Okay, so not something you have to memorize, but a quick little application. One of the quick things we can do is generally we can approximate the drag coefficient as a half. So much like the coefficient of friction, this is a dimensionless unit, meaning that it has no unit. And for many things, the drag coefficient falls between a half and 1. So for our calculations right now, we're just going to say it's a half. And that gets us one quick formula where the velocity is the square root of 4 times mass times gravity divided by rho, the density of the fluid, times the cross-sectional area. And honestly, that's about as deep as we can get with it right now because of the concept of differential equations and how it applies to this mathematically. So that's all we're going to take a look at. So we got a partner problem that we'll take a look at in class. But it says a 75 kilogram skydiver and his 20-gram pet mouse jump from a plane. Estimate their terminal speeds, assuming that they both fall in a prone position. So the only things that matter, according to my previous slide, are mass, gravity, rho, which is the density of the fluid, which I can actually, it's a constant for air, and their cross-sectional area. And the best way that we can approximate their cross-sectional area is by thinking about them as a square or a rectangle, however you want to think of it. And that's what's going to encompass or encounter all the drag force. So we'll take a look at that in class, and we'll solve that in class. And then we're going to finish off this chapter by taking a look at a couple different applications of Newton's laws and how they apply to very specific situations. Now that we're done getting a basic category of forces and how we can quantify those forces with equations. All right, so the next lab that we're going to take a look at is called determining mu. And for those of you who don't know, this is over on the left over here. This is mu, Pokemon number 151 on red-blue versions, the original versions. And the only way you could get it during the game was to use the Golden Nugget Bridge glitch. Where you have to like go up the bridge, then you go and talk to somebody, but then exit the game, and then or teleport during the game. It's actually a really tough glitch because you have to catch an Abra before you can do this glitch, and the Abra's only move that it knows at that level is teleport. So you have to get lucky enough to catch that Abra, and then you can do the glitch. So it's actually very difficult. But good luck if you want to check it out. So for this one, this happened to be the felt for me. The maximum force for the felt on the table was 3.5 newtons, and the force of constant velocity was 2.5 newtons. And to get the coefficients, all I need to do is plug it into these equations. So it's F max divided by the normal force. Well, in this case, the normal force is equal and opposite to the weight. So if I take the total weight of my apparatus, which in this case I included 2 extra masses, you can totally do that if it helps you get better results, but the coefficient stays the same. So I would just have to mass this out, divide my 3.5 newtons divided by the normal force, which is equal to the weight, and that would get me my coefficient. And again, this is a dimensionless unit. So I'm going to do this for 3 different things. The felt on the table, which is what you just saw, the cork on the table, which uses the little like boxes or boats, and then the wood on the table, which I can just take my, there's wood ones over available, or I could just flip my felt one over.
The felt ones, there's only 3 of them, 4 of them, sorry. So just make sure you're sharing with your classmates once you gather the data. We'll post lab this a little bit on Monday or on the next day, and we'll talk about it then. All right, but other than that, it's a really simple lab. So good luck. Okay, so we've finished talking about more in depth the formulas for different forces and how they differ, like static and kinetic friction and stuff like that. So now the last 2 sections of chapter 5 are just a couple applications of Newton's laws. So 5.7 is about interacting objects, which is kind of a confusing in-depth look at Newton's third law. So there might be some things that you don't quite fully understand, but that's okay. Newton's third law can get really complex. So we'll just have a brief little discussion about it now and go on from there. So a quick little review. Newton's third law states that all forces occur as an action-reaction pair. So they recur as an action-reaction pair of forces. They always act on different objects. So if object 1 pushes on object 2, then object 2 pushes back on object 1. But the 2 members of an action-reaction pair are they're going to point in opposite directions but have equal magnitudes. And we kind of took a look at that before, so now let's spend a little bit more time talking about that now. So here is an example of there's a hand, and that hand is pushing box A. But as it pushes box A, if we were to look at analyzing A's motion, we would have to understand all the forces acting on it. So A is being pushed on by the hand. So if I were to draw a quick little free body diagram, there is a push of the hand onto A, as well as, of course, the weight and the normal force. And that's going to cause acceleration. But the other thing we got to kind of think about is how much it accelerates isn't just based on A's mass, but also based on B's, because we need to think about that as A pushes on B, B, according to Newton's third law, pushes back on A. So there's this force of B on A right here. And if we do the same thing with block B, now it's got its weight, which is larger than A's, its normal force. There's the force of A on B, but it's also going to push back on A. B on A. Okay, so as we look at these, the forces on A and B, they're not independent on each other. The force that B on A, so the block B acting on block A, and the force of block A acting on block B, they're an action-reaction pair, and therefore, since they're in contact, they have to have the same acceleration. And that makes sense. Like, these 2 objects are connected to each other. So as I'm pushing one, because there's that action-reaction pair, the other one must also be moving. But the point is that we can't solve for the motion of one of the block without considering the other one. If block A was the only block there, it would accelerate at some rate. But since block B is also there, it's also causing forces to act on A, and we have to take in that account. Okay, so what does that mean? Well, let's go. It means that we're going to have to start considering not just the mass of one object, but you'll see me, especially as this unit continues, that the force, the net force, it no longer equals the mass, but it's the mass of the system, not times the acceleration, but times the acceleration of the system, which seems kind of trivial that I'm just adding those subscripts. But if I think even back to the Atwood machine experiment where we had the masses hanging off the edge of the table, those masses and the cart accelerated at the same rate. So as we think about Newton's third law, that's what we're going to have to consider, is that all the forces act on a system, and as I increase the mass of the system, the overall acceleration will decrease, and we'll talk about that a lot in the last section, which is on ropes and pulleys. All right, so here's a quick check. considering the situation in the figure, which forces is an action-reaction pair. So I have all these forces going on, which is actually really confusing. But I have to look and say, if A acts on B, B acts on A. So which one is the action-reaction pair? As I go through the options, the normal force on A due to B and the weight of A. So A has this force going downward, and B pushes back up, and that is why B is the correct answer. Taking a look at the other ones, the tension of the string and the friction acting on A. A is pulling, or the string is pulling on A, then the action-reaction pair would be A pulls back on the string. So that one's not it. The normal force on A due to B and the weight of B. So B pushes up on A, but then B also goes down. That's not an action-reaction pair. And finally, the frictional force acting on A and the friction acting on B. Those are two different objects, so it's not an action-reaction pair either. All right, here's another one. Boxes A and B are being pulled to the right on a frictionless surface. This is getting back into what we're talking about. Now, tension 2 is pulling both block B and block A. Tension 1 is being pulled on by B, but it's only pulling block A. So therefore, tension 2 is actually greater than tension 1. So these can get kind of confusing as we get into talking about that, but we'll summarize that up in just another minute. Here's another ranking task. So boxes A and B are sliding to the right on a frictionless surface. Hand H is slowing them down. Box A has a larger mass than box B. So we know there's an action-reaction pair with the hand on block B. So those have to be equal and opposite. So B on the hand is equal to the hand on B. But then A is pushing on B, so B has to push back on A. And those are an action-reaction pair. But since the hand is causing the acceleration, that's going to be the greater of the two forces. All right, so this is the last section in Chapter 5. Now, if you got confused by the previous section, this is an application of it, and hopefully it makes a little sense. A little bit more sense, rather. Not little, but a little more. So what I kind of tried to get at last section was this concept that the acceleration is the net force divided by the mass. But I want to modify this and instead say the acceleration of the system is the net force divided by the mass of the system. And the reason that I'm going to do this is because I have multiple objects now that are going to be acting. So I want to make sure that if those things are linked together, because they're an action-reaction pair, they're going to experience the same acceleration because they're all part of the system. So let's take a look at what that means. So when I think about something like a rope, we've already looked at that. We've looked at that concept of tension. Essentially, the tension is it's the force that's exerted on the box, okay? But therefore, there's also a box exerting the force of the tension, and those two are equal and opposite, and that's what causes the box to move. Now, that probably sounds really stupid, but essentially I'm saying that I'm pulling on the rope is pulling on the box, so the box moves. Now, most of the time in physics, we assume that the rope is massless, but there may or may not be a test question where we do not make that assumption. And because you guys are all so great at watching the videos, I'm going to give you a little hint right now, and that is if I have a mass tied here, and let's say that this is 100 Newton weight. We'll just say it's 100 Newtons. And the weight of my rope, let's say it's a really long rope, and the rope is not massless, but I'm going to say that the rope is tied off right here, and the weight of the rope is 50 Newtons. I don't remember exactly what the numbers are, but this I think this is right. Yeah. So my question is, what's the tension then in the rope? And the answer is kind of weird, but right here where it's tied off, at this point, the tension in the rope is 150 newtons. And that might not make sense because you're like, no, it's only holding 100 Newton mass. But at this point in the rope, it's also supporting the entire weight in the rope. It's hanging down from it. So it's 150 newtons. At this point in the rope, the tension is 100 newtons. And everywhere in between, it's somewhere between 100 and 150. So like right here in the middle, it's supporting half the rope, so it's 125 newtons. Anyway, that's a free test question for those of you who watch the videos. You're welcome. But it's just saying that normally in physics, we assume that the mass, normally in physics, we assume that a rope is massless, but I give you one test question where you got to think about that, what happens when it's not. Okay, so we got a quick check here. And this is starting to identify the concepts of these action-reaction pairs and how they relate to the acceleration. So here I have 3 50-kilogram blocks, but they're all at rest. And that makes sense because if they're the same mass over here, then they're going to have no net force. Now, as soon as one of these are in motion, it gets a little complicated, but yeah, it's going to stay in motion. So if I were to push this 50-kilogram box, it's going to move and it's not going to stop moving because the object is in motion, okay? But anyway, right now, we're in static equilibrium, and therefore the net force is equal to 0. So in both of these cases, I should say in all 3 of these cases, we have identical free body diagrams where the tension is going to be equal and opposite to the weight, and therefore the tensions are all the same. Now, when the object is in motion or the masses aren't the same, that's going to change the tension because that will show how we'll get acceleration, and we'll take a look at an example problem like that this section. Okay, so pulleys, this should look really familiar because this is essentially our Atwood machine that we did our lab on. But we're going to continue to assume that we have massless strings, so we don't have to worry about those mass. And it's going over this massless, frictionless pulley. So when we look at that, there's no friction. This is known as an ideal pulley. And what that means is if B has some weight that it pulls down, let's say it's 50 newtons, then A has some force applied of 50 newtons. So it's how we just say that there's no friction being lost in this pulley, so that this is 50 newtons, but this is actually 48 newtons or something like that. So in a frictionless pulley, an ideal pulley, whatever weight we apply is what we should get the box to be, box A to also experience. That might have been a cause for error in your lab, but we'll assume that for our physics problems that they are perfect or ideal. So I got a quick check. The top of the block is accelerated across a frictionless table by the falling mass m. The string is massless and the pulley is both massless and frictionless. What's the tension in the string? So this is an application in Newton's third law, but there has to be an acceleration downwards, which means that there has to be a net force downwards, which means that the weight mg has to be greater than the tension force. And the reason that makes sense is because this the mass this force right here needs to outweigh the tension to give me the net force. So in this case, the tension has to be less than mass times gravity. Now, if it were going at a constant velocity, or if it were not moving, then the tension would be equal to mass times gravity. And if it were slowing down, like imagine, I don't know, like if you've seen The Matrix where he's like, they're on the top of the building and Neo like tries to grab the helicopter by a rope as it's like falling, then the tension would have to be greater because he's causing the helicopter to accelerate upwards as it's falling down. Okay, so we got an example problem, and this example problem is called lifting a stage set. And this is an application of ropes and pulleys. But it says a 200 kilogram set used in a play is stored in the loft above the stage. So if you've ever been to like a playhouse or like whatever you want to call it, they have multiple backdrops, and they change the backdrops by a pulley system. Now, normally there's pulleys that create mechanical advantage, and we could talk about this, but it's not really something that's covered in our scope and sequence, but it is a physics thing where you have what's known as a block and tackle pulley or double pulleys. There's all types of different types of pulleys that we could get into a ton about, but they create mechanical advantage. But anyway, the rope holding the set passes over a pulley and then is tied backstage. So if I have a 200 kilogram set and there's only one pulley, there's no mechanical advantage, but the director tells a 100 kilogram stagehand to lower the set. When he unties the rope, the set falls and the unfortunate man is hoisted into the loft. What is the stagehand's acceleration? So let me see if I can draw a picture of this real quick. Here's the stagehand, and he's holding onto a string that's attached to a mass. We'll just call it a mass because I can't draw a full, backdrop. And we'll call that 200 kilograms, and he's only 100 kilograms. So if I were to take a look at these free body diagrams, this guy's got a weight going down, and this mass has a weight going down, and it's much larger than the man is. And the mass is tied to this string, which the only counteracting force of this string then is the guy's weight. Okay, so but looking at the guy's weight, the counteracting mass is the counteracting force is the weight of the heavier object. So in this case, there is going to be a very large tension going up that is in fact larger than the weight of the man, but it's equal to the or it's caused by the weight of the set. So there's also this tension right here, and since this is an ideal pulley, and these two things are attached to each other, then these two tensions have to be the same. Okay, so let's go to the next slide where I have this drawn a little bit neater. Okay, so here is the a better picture, and we have a free body diagrams. Now again, I'm gonna say, and I talked about this in class a little bit, when we get into these types of weirder situations, which we won't spend a lot of time on, I'm gonna go ahead and say that this is the positive x direction. So now as I start to quantify stuff, I'll keep that in mind. So here's what I'm looking at. I want to find the acceleration of the man, which is going to be the same as the acceleration of the set. So here's how I set this up. I can say that the sum of the forces, I can call this, my picture has it as the y direction. I just said this is positive x. Let me just change that to positive y. So the sum of the forces in the y direction is equal to the net force in the y direction, which is equal to not the mass anymore, but the mass of the system times the acceleration of the system. So anytime I have interacting objects or multiple objects, that's how I'm going to call it. I'm going to call it the mass of the system times the acceleration of the system. So when I look at the forces, the sum of the forces, the force going in the positive y direction is going to be the weight of the set. So the weight of the set. And then that's going down, that's right here. Then I have the tension of the set is in the negative y direction. But then the tension on the man is in the positive y direction. And finally, the weight of the man is in the negative y direction. And these things are going to be equal to the mass of the system
times the acceleration of the system. Not the set, but the system. So don't confuse that. That's SYS. Awesome. SYS. Kind of running out of room. So these two tensions, since they're part of an ideal pulley, they actually cancel out. And I get the mass of the system. I totally just screwed that up. Mass of the system times the acceleration of the system equals the weight of the set, which is the mass of the set times gravity, plus, minus, struggling here, minus the weight of the man, which is the mass of the man times gravity. Okay, so now I have to solve for the acceleration of the system. So let me just clean this up real quick. All right, so to get the acceleration of the system by itself, it's going to be the mass of the set times gravity minus the mass of the man times gravity divided by the mass of the system, which is going to be the mass of the set plus the mass of the man. Okay, so like I said, the big concept is the sum of the forces equals the mass of the system times the acceleration of the system. And this kind of makes sense because the set is acting like a weight in free fall, but the man is acting like a counterweight. And the larger his mass, the less the acceleration. And it's not just about how close these masses are together, like a 2 kilogram and a 1 kilogram mass. It's about the total mass as well. So I'll talk more about that in class, and there is a test question on that gets a little confusing, but I'm pretty sure I'll probably put it on the day before the test, and we'll talk about it. So the mass of the set is 200 kilograms times gravity, which is 10 meters per second squared, minus the mass of the man, which is 100 kilograms, again, times gravity, which is 10 meters per second squared, and then that whole thing over the two of them combined, which is 300 kilograms. So I have 2,000 minus 1,000 divided by 300, and I get an acceleration of the system of 3.33 meters per second squared. Okay, so the system accelerates at a steady or a constant 3.33 meters per second squared. And here it is again, probably a little bit nicer written out. But a quick little note: if the stagehand wasn't holding on, then this is actually a lot easier. There is no countermass, so there is no tension, and then the only force is the weight. Well, that's just an object in free fall. So essentially, what's happening is the man is acting as a counterweight, and the heavier that man, the slower the acceleration of the system. And that's actually going to do it as an introduction to this. And like I said, it's an application of Newton's third law, and then it ties into the other Newton's second law and Newton's first law. So it can get a little confusing. Luckily, like I said, this is not a heavy hitting point. It's just getting into some of the applications, which when you get into physics, like my goal is to give you and show you some of the applications, not necessarily to make sure that you understand and can execute them all, but to understand why or what they can be used to do. But that wraps up chapter 5. So we're going to do a lab, and then we're going to go tie in chapter 6, which is all about an application of forces and looking at going in uniform circular motion and taking a look at what's known as the centrifugal or centrifugal force, and some of the really cool applications of that. And we'll do that in the next segment. All right, so as we continue through Unit 2, we've done Chapter 4 and 5, which are all about Newton's laws. And now Chapter 6 is going to be the last part of this unit, and that has to deal with circular motion, orbits, and gravity. So it's actually more of an application of Newton's laws than it is just learning about Newton's laws. But it's a big part that is covered on the AP exam, and if you've taken a look at your practice FRQ yet, you would see it in there as well. Okay, so we are starting with a pre-lecture video talking about forces and apparent forces when dealing with circular motion. So when we talk about Chapter 6, we're talking about uniform circular motion. And uniform circular motion can be a little misleading because we're going to say that any object has acceleration, and therefore it has a change in velocity, even though the speed is constant. So you got to be careful when we're discussing these things, but we'll take a look by starting at with the pre-lecture video. Okay, so he starts off by whipping a ball around in a circle, and he recapped just what I was talking about in this video about how an object that goes around in a circle, so if here I have like a ball tied to a string, it's going with some velocity, and the overall magnitude of the velocity, aka the speed, is constant, but since the direction is changing, then the velocity itself is also changing. And so the speed, and this is what gets confusing, the speed is constant, but due to a change in direction, we have to have a change in velocity, and that means we have to have acceleration. And in this case, the acceleration is always pointed directly to the center, and it has a magnitude of v squared over r. And this was introduced way at the end of Chapter 3, and that's what we're going to be focusing on more right now. So then he continues to go through a couple different demonstrations, like having a cup of water on a platform as you're spinning around in the circle, and getting into the apparent forces that are acting as something goes in a circle. So it is a good little video. It's a good little introduction of some of the stuff that we're going to cover in this chapter. The first part of this chapter is the easy, straightforward part where we're just defining and explaining uniform circular motion. So that's where we're going to start. So uniform circular motion is just an object that's going around in a circle. So on the right side of the page over here, I have exactly that. We have this so we have this dot right here. It's going around in a circle. We can see that by the lengths of the vectors that the velocity is constant, or I should say the magnitude of the velocity is constant. So as we look over to the side, we're saying that the speed of a particle is constant, but because it's changing its direction all the time, the velocity is not constant. The velocity is changing. And we actually got this at the end of Chapter 3 in a quick little introduction, but we have this formula that the acceleration is the velocity squared over the radius of the circle. So here's my center of the circle. This is the radius. Here is the velocity. Velocity in meters per second, radius in meters. We get, and then velocity is squared. So we get meters squared over seconds squared over a meter. One of the meters cancel. You'll typically see me write it as this: a subscript c is v squared over r, indicating that it is circular motion. And that's a centripetal acceleration. So got a little quick check for you. Ball's at the end of a string is being swung in a horizontal circle. This means like it's on the ground, or it's facing the ground and it's circling above the ground, versus thinking about like in the pre-lecture video when he was demonstrating twirling it around where something's going above my head and then below my head. So if that makes sense, I can try to draw it real quick. It's doing this, there's my string, and there it is going a circle, versus this, oh wow, that was great, where it's going up and down in a circle, right? Anyway, long story short, So it says the ball is accelerating because, and the answer is the direction is changing. So it's being swung in a circle, speed is constant, but direction is changing, so velocity changes, and therefore we have an acceleration. Another quick check, car is turning a tight corner at a constant speed. Top view of the motion is shown below. The velocity vector, we're going straight right here. Technically, that's going to change as it continues to go around the circle. Points east, what's the direction of the acceleration? Well, this is the radius of curvature. And for circular motion, the direction of the acceleration is always directly towards the center of the circle. So the direction in this case is going to be south. So when we're talking about circular motion, we have to think about how we're going to describe things. Now, before, we had things like meters per second for speed and acceleration. We had all these different things that our units made sense. But now we're going to change up our vocabulary because our view has changed up. So we're no longer looking at linear motion. So we need to describe things in a new way. So the first way, we'll talk about the period of an object. And the period is how long it takes the object to go around the circle one time. We use the letter T for that, the capital letter T, and it's to go around one time or one circumference. Now, we also use something known as frequency, and if period is the amount of time that it takes to go around once, the frequency is the number of times it makes in 1 second. And these two quantities are inversely related to one another. So we can easily convert from one to the other. But these are some different ways for us to quantify and explain what is happening with the motion of the object. When I look at a tire, I don't say it's traveling at 32 meters per second. I say it's rotating at 200 RPMs or something like that. That would be an example of a frequency. Or it takes a tenth of a second to go all the way around. That would be a period. Thinking back to Unit 1, I know that velocity is distance over time. So my distance in this case is 1 circumference, and the time is the period. So I get this new equation for velocity that's 2 pi r over t. And if I go back to the previous slide and I say, well, frequency is the inverse of the period, then I get another equation that velocity is 2 pi fr. So there's two different ways to find the instantaneous velocity as the object goes around in the circle. So the instantaneous velocity is going this direction, but based on the period and the frequency and this radius, I can tell you how fast it's going. Then the last step, so this is just getting us into some quantification stuff. I know that this centripetal acceleration is v squared over r. If I take my two equations for velocity and plug them in from the last slide, I get two more equations for acceleration. So really, we just made a huge bank of ways to quantify it, which means really nothing to us yet, but until we actually start talking about it, but just want to have a few different ways to quantify motion. Now, there's one more way to describe how fast something moves that's independent of where that object is on the circle, and that's its angular velocity. And if you've taken pre-calc, you've probably dealt with angular velocity a little bit. We're going to do very, very, very little with it right now, but we're actually going to come back when we do rotational motion and talk a lot more about it. So when something's moving in a circle, we can describe how fast it's moving or rotating in radians per second. From trig, 1 revolution is 2 pi radians. So this actually gives us two more equations. Like I said, we'll use this very limitedly right now, but we will come back to it a lot more later on in Unit 5. So just to give us one quick conversion example, if I want to go 55 revolutions per minute to angular velocity, well, 55 revolutions in 1 minute is RPMs. But angular velocity is measured in radians per second. So 1 minute is 60 seconds, and 1 rev is 2 pi radians. And if I go ahead and plug that into my calculator, I get about 5.76 radians per second. So it's a different way of quantifying our circular motion. So this is saying how fast it spins. This is saying how fast it's spinning, which might say the same thing, just in a different way. All right, so we got one quick example problem, and it says an audio CD has a diameter of 120 millimeters and spins up to 540 revolutions per minute. When its CD is spinning at its maximum rate, how much time is required for 1 revolution? And if we have a speck of dust riding on the outside edge of the disc, how fast is it moving? What is the acceleration? So this question is actually giving us a lot of information and asking us a lot of questions. So just to set up a couple things, it says that our radius is 120 millimeters. That means, or I'm sorry, it's diameter. Well, then that means the radius is 60 millimeters. But we know right away that that's not a very good thing to take a look at. That is instead 0.06 meters. 500 RPMs, 540 RPMs. Well, that's a type of frequency, but normally we don't want to deal with things in minutes. So I'm actually going to convert that to our period, which is how long it takes to go around once, which is 540 revolutions in 1 minute. And 1 minute is, of course, 60 seconds. So I get a frequency of 9 revolutions per second, or we call that 9 inverse seconds, but that's going to be our frequency, and we'll use that to solve for the period. And then we're also we're looking for time, we're looking for velocity and acceleration. So with a couple little background, let's go ahead and take a look at that. So here, once again, I'm solving for my revolutions per minute, or my frequency, and also I did my diameter right there, and we'll use that on the next slide. And to solve for this then, time for 1 revolution was one of the first questions. That's our period, and we said that our period and our frequency are inversely related. So I just take 1 over the frequency to get the period, and it's 0.11 seconds. The next question was, how fast is the speck of dust moving? That's its velocity, and I have a bunch of equations now for velocity that I can think about, and I chose to use this one, but we could also use the 2 pi r over t to solve that as well. But then I just plug in, and I get 3.4 meters per second. So if you think about it, taking a look at the top down of a view of this is a CD, believe it or not. It could be whatever kind of CD you want. But if I'm a speck of dust right here, I am traveling at 3.4 meters per second. Now we'll talk later on this unit and a different unit. How does that place compare to this place? And going from the outside edge to the circle, how does that change how fast you're going? Well, just a little spoiler alert, if I think about this is the distance that this one travels, and this is the distance that this one travels, but they do so in the same time, this place on the outside edge is going to have a much higher velocity. We'll talk about that a lot later. And then finally, the acceleration, using our equation for that, we get 190 meters per second squared, which is actually really, 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 really large. And if you think about that, that's how the human centrifuge works, and we'll talk more about that this unit as well. But other than that, that was your quick introduction into circular motion. We're going to spend a lot of time talking about how we use forces to quantify circular motion, as well as some of the other applications of it in dealing with things like weightlessness and planetary motion as we build our concepts throughout Chapter 6. All right, so we started Chapter 6 by taking a look at the kinematics involved in circular motion. Now, the next thing that we'll look at is we're actually going to start to evaluate the dynamics or the forces involved in circular motion. So, pre-lecture video 2,
is your first introduction into that. In this video, there's 3 different examples that he talks about. He talks about a car going around a portion of a semicircle. So if I were to think about, here's my curve, and the car as it's right there, if I were to draw a free body diagram, there has to be some acceleration towards the center of the circle, which means there's a net force to the center of the circle. And he talks about how that's the force of static friction. And then he also talks about the frontwards view, and we could think about that as like a runner as they're going around the circle in a track, and how there's this natural tendency, sorry, it's not quite working, not quite what I wanted it to be, but as they go around the track, there's a natural tendency to lean, and that's because there's a normal force going up and to the right because your weight is going down, and you need this static friction, to help you turn. And it's the same thing with the car. So he gets into a little bit of the free body diagrams behind going around the radius of curvature, both in a car and as well as running. Then he evaluates one last type, which is what if we're going over a hill. So we'll take a look at hills and we'll take a look at dips. And these are portions of semicircles as well. So if I'm at the top of a hill, my acceleration is towards the center, so my weight has to be larger than my normal force. And if I'm going around a dip, again, center of curvature, so now my normal force has to be larger than my weight. But when I take a look at these 2 examples, I get different feelings of weight and apparent weight. And we'll talk about those throughout this chapter as well. Okay, so the next section of chapter 6 is dealing with dynamics of circular motion, specifically of uniform circular motion. It says part 1 here. We're actually going to combine this into one section, and it's actually pretty quick because we do have some partner problems and stuff that we'll take a look at, but we'll do those during class. So we're looking at dynamics of uniform circular motion, or the forces involved with circular motion. So here is, again, our picture of something going around the track now, or going around a circle over on the right over here. So we already drew this kind of last section, but that means if there's an acceleration towards the center of the circle, that means there has to be a net force to the center of the circle as well. And that net force, as you see on the left, net force is always mass times acceleration. Well, acceleration, we said, was v squared over r. So the net force is mv squared over r toward the center of the circle. This is not a new kind of force, but it's still that net force. It's going to be caused by another force. It can be caused by tension, like when I have my keys spinning around, friction, like if I'm making a turn, or even the normal force. That's also can help me provide this centripetal force. So we'll talk about the concept of the centripetal force as we go through this chapter, but this is taking a look at when I have centripetal acceleration, there has to be some type of force that's causing it. And the magnitude of that force is mv squared over r. So I got a quick check. A ball is at the end of a string being swung in a horizontal circle. So if I were to kind of draw that out real quick, that's me holding a string out to the side, and then it's kind of swirling around above the ground. And the question is, what force is producing this centripetal acceleration? It's going to be the tension in the string. The tension is what's causing it to stop. If I let go of the string, this would fly off to the side because that tension is no longer there. All right, another quick check. The ball is at the end of the string being swung in a horizontal circle. The direction of the net force, the acceleration is always towards the center of the circle, so the force is also always towards the center of the circle. So this is a quick little video. It's kind of silly. Self-mowing lawn. We have a lawnmower on a string. So the lawnmower just wants to go forward at a constant velocity. So the string is providing a tension that causes this uniform circular motion. And as you can see, we got these nice centripetal circles, or what's the word? Centric circles? Yeah, that his lawn is mowed with. So it's a silly little video that demonstrates that.
Another quick check, hockey puck is tied to a string but to a stake in the ice. The puck is then swung in a circle. Force is producing this centripetal acceleration. Again, it's going to be this rope right here. There's this tension that's causing that to go in a circle. Another quick check, the coin's rotating on the turntable. It moves without sliding. That's the instance shown, which following gives the directions of the following. So right now it's rotating counterclockwise, this direction. So the instantaneous velocity is going to be right here. It's going in this direction. That's point A. The frictional force is actually kind of a weird thing to think about, but it would go forward, and there's a direction of an acceleration, and that's towards the center of the circle. So this D right here is actually the direction of the frictional force, which in this case is providing the centripetal acceleration. And then if all of a sudden I got rid of this frictional force, then the instantaneous velocity, which is A right here, is going to be the direction of motion. All right, so we got a quick little conceptual example, and we're going to take a look at this more later, but it says engineers design curves on roads to be segments of semicircles, or circles. They also design dips and peaks to be segments of circles with a radius that depends on expected speeds and other factors. So when you engineer a road, how tightly it turns is very carefully thought about. It says a car is moving at constant speed and goes into a dip on the road. At the bottom of the dip is the normal force of the road on the car greater than or less than or equal to the car's weight. So if we were to take a look at a free body diagram of this, we can see that at the dip of the road, and this is obviously way over exaggerated, there has to be an acceleration upward. If there's an acceleration upward, that means that there also has to be a net force upward, because if the acceleration is towards the center of the circle, then the net force must also be towards the center of the circle. And if that's the case, then the normal force has to be larger than the weight of the car. And how do you feel when this happens? Well, you can think about it as like on a loop-de-loop. And on a roller coaster, at the bottom of that loop, you feel like you're being compressed. You feel very, very heavy. And that's because you have a larger normal force. And as we learned in chapter 4 and chapter 5, the normal force is equal to your apparent weight. So if you have a larger normal force, you also have a larger apparent weight. So this is just summing it up. Again, your normal force is larger than your weight, so you appear heavier. Now there's another example. What about if we're going around a turn, and let's get a top view of going around a turn. It's turning a corner at a constant speed while following the segment of the circle. What force is necessary to provide that centripetal acceleration? So the centripetal acceleration has to be in towards the center of the circle. And my question is, what force is providing that? And we know that there's a net force because there's acceleration. And he talks about this in the pre-lecture video, but the force that's allowing the car to make the turn is the force of static friction. And you might think that that's weird because it's not stationary. But if the car was turning without static friction, it would slide, and then it actually wouldn't be able to turn. So kinetic friction is actually what makes drifting possible. So it's the tire slides side to side during drifting, but when turning, it doesn't slide at all. So it's static friction. A great example of that is hydroplaning, and there's a lot of videos out on YouTube, and I've seen some are better than others, but the concept of hydroplaning is I'm going at some velocity, and due to a lack of friction, my car starts essentially drifting. And what that means is that I have broken static friction. So you might experience this, especially when it's heavy rain, especially when it first starts raining. When you experience it is when you're accelerating. So in some of these videos, you see people taking turns, and that's when they start losing it because they need that centripetal acceleration and that static friction to allow them to turn. So a really interesting application of losing that force of static friction. All right, we got a quick check. A hollow tube lies flat on a table. So this is actually a view from above. It's kind of misleading. This is a top-down view. The ball is shot through the tube, so it's coming around what happens when it leaves the tube? Well, the instantaneous velocity is this direction, so it's going to follow path C. Now, it can't follow paths B or A because all the way through as it's going around, it's pushing against the wall. So there's actually a normal force that's pushing it into the center of the circle, and that's what's causing that centripetal acceleration. Once we get rid of that by losing the wall, it's just going to go straight. It's going to go in the direction of its instantaneous velocity. All right, so we got a real example, and this is the hammer throw. And in the track and field event known as a hammer throw, athletes spin a heavy mass in a circle at the end of the chain. Once the mass gets moving at a different speed, the athlete lets go, and then it follows in a parabolic arc. So the person actually stands here, and they hold this chain that's attached to this really heavy object, and they spin around in a circle, and they let it go. And when they let it go, the instantaneous velocity goes off into the instantaneous velocity goes off into whatever direction it was being thrown at, and then it follows this nice trajectory similar to a projectile motion problem. So it says that the hammer is a mass of 7.3 kilograms at the end of a 1.2 meter chain, and it says a world-class thrower can get the hammer to a top speed or instantaneous velocity of 29 meters per second. And if they're swinging it in a horizontal circle, what's the tension in the chain? And well, the tension is what's providing the net force and the centripetal acceleration. So that's equal to mv squared over r. And if I plug that in, that's about 5,100 newtons. That's the same as holding a 510 kilogram mass, which is 1,000 pounds. The people who do the hammer throw have to have huge strength to get that velocity. So imagine, you keep spinning it faster and faster. It appears heavier and heavier. And when you get to this big of a speed, you get to that huge force, which is really hard to hang on to, which is why it's a tough event. This is a quick video. It's from the slow-mo guys, and they experiment with spinning a CD at faster and faster and faster RPMs, and that centripetal acceleration causes what we like to call, we'll talk about more later, a centrifugal force, and that's based on mv squared over r. So the faster you spin something, the greater the force it experiences. This gets into like the human centrifuge and a couple different applications that we'll talk about this unit. But they spin a CD faster and faster until it breaks, and then they take a look at the slow motion video of it breaking. So it's kind of a cool video, worth kind of skimming through. I don't know if I'd watch the whole video, but definitely worth a quick skim. So to recap, we have this net force. The net force is what's causing the centripetal acceleration, so I like putting that little subscript C, and that's mv squared over r, which is towards the center of the circle. So your first partner problem, which we'll take a look at in class tomorrow, it says what's the maximum speed at which a 1,500 kilogram car can make a turn around a curve of radius 20 meters on a level road without sliding. It says note the coefficient of kinetic friction is 0.8 and static friction is 1.0. Well, we said before that the coefficient of kinetic friction only matters if it's drifting. So I'm actually going to use the coefficient of static friction. And we'll take a look at this problem in class tomorrow, but we're taking a look at what causes the car to be able to turn. And engineers can actually use this formula to determine, based on a road, what the speed limit should be. So when you see those yellow cautionary speed signs, those are based on road conditions. And if you're something like a civil engineer and you have to determine those, you have to take a look at static friction and how that affects you. So we will take a look at this problem tomorrow during class. The answer is in the notes, but we'll talk about it more tomorrow. So here's another example problem, and this is very, very, very similar to the previous problem. So I'm not going to talk about it too much right now. It's actually a very specific example, but now we're on a banked road. And the question is, at what speed can I make the turn without the assistance from friction? And we just said that the car needs static friction to turn. But let's take a look at this problem real quick. Here, I have the normal force is coming off of the surface, which means that there's actually an x component of the normal force. So if I'm on a banked road, I actually don't just need friction to cause it to turn. There's this X component of the normal force that can allow me to turn. So when people calculate how fast they can turn, an example for like a NASCAR race, they take into account the radius or the bank of the road, and then they can increase their allocated velocity to go faster around that corner. So when you watch like a NASCAR race, as boring as it could be, they have everything calculated to their optimal velocities when they go around the track. There's a crazy amount of physics involved with that. So this is just going to go through the math behind it. So in the X direction, I have the X component of the normal force. In the Y direction, I had the Y component of the normal force and the weight. It's not accelerating up or down, so the net force in the Y direction is 0. The X direction is causing my centripetal acceleration. So the normal force equals the weight divided by the cosine theta, which is mg over cosine theta. And if I plug that into the other direction, this is the X component of the weight. That turns into mg tan theta, and that equals mv squared over r. The masses cancel, and the velocity is the square root of rg tan theta, and I get this maximum velocity. It's not important that you know how to do this problem. It's just a really great example of how we can determine those things based on the centripetal acceleration. So I went through that really quick. Again, it's not, I would never have you solve a problem like this. It's just a cool application. So we got another partner problem that we'll take a look at tomorrow, and this will be the last one. It says wind turbine, it's spinning, it's got 1,200 kilogram blades. They're 38 meters long. The blades spin at 22 revolutions per minute. And if we model a blade as a mass at the midpoint of the blade, what's the inward force necessary to provide each blade's centripetal acceleration? So we're just taking a look at what is the centripetal acceleration, what's the magnitude of it, and we'll take a look at that tomorrow. And that actually concludes our introduction into solving circular motion problems. Next, we'll take a look at the apparent forces, and we'll take a closer look at that net force concept of the F net is mv squared over r. And we're going to take a look at some of the applications as it appears or contributes to your apparent weight. So we'll do that in the next segment. All right, so the next part of this, we will continue to evaluate and quantify the forces involved in uniform circular motion. Now, in the last section, we just said that the net force is mv squared over r. We're going to continue to evaluate that now, but I'm going to refer to it quite often as, instead of the net force, I'm going to call it the centrifugal force. And the centrifugal force is not a real force. It's caused by other physics things that we're going to talk about in this section. So as I refer to it, understand that it is never to be drawn in a free body diagram. It is not an actual force, but it helps us understand why some things are happening to talk about it like it is a force. All right, so let's check it out. So what is the centrifugal force? Now, if I'm sitting in a car and that car turns a corner quickly, I get pushed. Here I am. I'm in motion here, and I'm going forward, and I feel like I'm getting thrown into the door, and the door provides a push back. That push back causes me to be able to turn. That is my net force. But what I feel is my body trying to keep moving ahead, and I feel as the car turns, I feel like I'm being thrown to the outside. That is the centrifugal force. It's not a real force. It will never appear on a free body diagram, and it's never included in Newton's laws. Okay? So what is it then? Quite simply, it's your inertia. And that's put very nicely on this picture here. My body wants to keep going forward, but the car is turning around me, so I feel like I'm being thrown out. But really what's happening is my body's in motion, and it wants to stay in motion.
So my inertia is what causes this quote-unquote centrifugal force. And then as I'm being thrown forward, the door pushes back on me, and that's what causes my centripetal acceleration. So as we're taking a look at circular motion, we do get additional phenomenons of apparent weight. And we've looked at apparent weight already, and we've said that apparent weight is equal to the normal force. So our normal force is what pushes back from the surface. And we can actually evaluate a few different things. Here we have a picture of a loop-de-loop. And again, our normal force is what's going to be the force that supports us. And that'll change based on a couple different factors. So let's take a look at two different points in a loop. So if I'm at the bottom of a loop, here is my free body diagram for what's going on. My weight is down. My weight is still straight down. But I have a normal force that's going up. And the net force, because the acceleration is towards the center of the circle, the net force is also to the center of the circle, which means that my normal force is larger than my weight. And if I look at the math behind it, then there's my normal force, there's my weight. The weight's actually in the negative direction, but those two forces have to equal my net force, which is mv squared over r. So my apparent weight equals my actual weight plus mv squared over r at the bottom of the loop. Now that's not right before or right after. It's strictly at the exact bottom point. And the reason is your weight changes as you go through a loop. The components of it change, and it makes it a little bit more complex. So we'll only look at the top and the bottom. But this makes sense, because if I think about in a roller coaster, I'm going to draw a really crappy roller coaster. I go up, I come down, and I go around this loop, and as I'm entering this part of the loop, I feel like my body's being compressed. I have a large normal force because of that centripetal acceleration towards the center of the circle. What about at the top of the loop? Well, if I'm going up, here's my loop again. At the top of the loop, my normal force is down and my weight is down. This gets way more confusing, but the sum of the forces is still my normal force and my weight. But in this case, they're both in the negative direction. So if I solve for my normal force, it's the net force minus the weight. Okay, well let's think about that. If the net force is equal to the weight, then this will actually become zero. And just for that brief moment, I will appear weightless if I'm going just slow enough that my normal force equals my weight. Okay. As I start to increase that velocity, I start to feel heavier. The faster I go, the heavier I go, or heavier I feel, I should say. And that will never, ever cap out. I can just feel heavier and heavier based on how fast I go. Now, it is important to mention, the last little concept is what happens when we have our velocity here, and this number is smaller than the weight. And the answer is, I can't go around the loop because my weight is pulling me down. So instead, I'm going around the loop, I can't make it, and I just fall. Okay? That would be a really crappy roller coaster. But we'll talk about that as it's known as the critical velocity, and we'll talk about that in this segment. So as the car goes slower, there becomes a point where the normal force becomes zero. This doesn't mean that there's no velocity. It just means that it's just barely fast enough to overcome gravity and make it around the loop. Any slower, and the weight of the cart would be too large, and the car would fall off the track. This is known as the critical speed. So when they are exactly equal to each other, I can set them equal to each other, and I get this equation that the velocity, I call this the critical velocity, equals the square root of GR. That'll actually come up a couple times, but that is the minimum velocity needed to make it around a circle or a loop. So we're going to take a look in class tomorrow, just a quick little demo where I drop a ball and it rolls down an incline,
And depending on how high I drop the ball, it may or may not make it around the loop. So it might make it to this and then fall straight down. It might make it only to here and fall down and back. Or it's going to just barely make it around the loop and then go all the way around. And that's the critical velocity. So we'll take a look at that tomorrow. This is a great video. I vote we watch this tomorrow. Someone just remind me just in case. So hopefully someone is watching this video before class and they say, hey, let's go ahead and watch that video. As a matter of fact, just go ahead and raise your hand and say, hey, don't forget to watch the video, and I will give you some, I'll give you 5 points of lab extra credit if you are the first person to tell me to watch the video. Just a little encouragement for you as we start the day off tomorrow. All right, so here's a partner problem, and this is just going to utilize that concept that the critical velocity, CRITI, oh my God, equals the square root of GR. Okay, so that's what we just derived a couple minutes ago. And it says a handful of professional skaters have taken their skateboard through an inverted loop on a full pipe. Here's our diameter. What is the minimum speed that a skater must have? And that's going to be utilizing this equation right here. We'll take a look at that tomorrow. Here's another quick check. We have a physics textbook swings back and forth as a pendulum. Which is the correct free body diagram? Well, as I know, I have a weight force going down and in this case, a tension force going up. There has to be a centrifugal acceleration because it's going around a curve, which means there has to be a net force, which means that the tension has to be greater. And this actually makes sense. The faster you swing a textbook, the more tension there is in that rope, and eventually it could break. But that is that concept right there. Another quick check. Now we're going over a hill. So I have a larger downward force because it's, again, the direction of the net force. And as I go over the hill, your weight is larger than your normal force, and you appear to be lighter. So, and tomorrow, we'll take a look at going over a hill, going in a dip, bottom of the loop, top of the loop, 4 specific examples about apparent weight. A huge application of this quote-unquote centrifugal force is a centrifuge. A centrifuge is a machine that rotates very, very, very fast, and because there's this inertia of the fluid or whatever it is you're analyzing, it actually separates out based on mass, because the different masses experience a different force, and that leads into density, because density, of course, is mass over volume. So something with a heavier mass experiences a greater force and gets pushed to the bottom. And this is how they separate, for example, they separate blood from plasma. Plasma is more of a liquid or a less dense fluid. So it separates out because of those different forces. One of the ways you can actually try this yourself is if you spin your own arms around your body extremely quickly. This causes the blood to undergo a quote-unquote centrifugal force, and it gets pushed out to your fingertips. And if you do this, that'll actually cause your fingertips to turn like a brighter red. One of the survival skill, I guess, if you will, if your fingers are losing feeling because you're stuck in the wilderness, this gets into, I believe, oh God, who is it? Is it? I think Jack Frost is not right, but it's a Jack something or another. It's a short story. Oh man, Jack. It's a short story about a dude in the wilderness. He's like trying to get into find a gold mine, and it's like going through the Yukon Territory. It's all about starting a fire. In fact, that's what it is. It's called To Start a Fire. I got it. To Start a Fire by Jack London. I'm pretty sure that's correct. Again, if you remind me, I will maybe I'll pull up a quick little video of this short story. The video itself has no dialogue in it, or very little dialogue in it. But what was I talking about? Oh yeah. So if your fingers are going numb, spin them around in a circle, get the blood flowing, and then you could hold a match to start a fire. I apologize for that minute and 26 second. What's the word I want? Trailing off, side conversation, whatever. All right. So here's a quick little conceptual example of an ultracentrifuge. Now, an ultracentrifuge just like a regular centrifuge, produces this centripetal acceleration. And these actually can create a centripetal acceleration of up to 250,000 Gs. And they do that to separate out different samples. So they can have this 3 kilogram sample, which only weighs 3 grams, and it spins at about 50,000 RPMs, and the math is all right above it to understand what you have to do to get that acceleration based on the frequency and centripetal acceleration, of course, v squared over r, but also getting into the concept that acceleration is the quantity of 2 pi f quantity squared r, and that actually solves for how fast it has to rotate. And then the apparent weight of that sample is actually 7,400 newtons. 7,400 newtons, that's 740 kilograms, which is over 1,500 pounds. So a 3 gram sample undergoing this feels like it weighs 1,500 pounds. And that's how they're able to create such that large force to separate stuff out. So that's just like I said, it's examples and just explaining what this quote-unquote centrifugal force is. And it's not a real force, but it's something that gets felt because of your inertia. So we'll take a closer look at this again tomorrow, and we'll talk a little bit more about some of the applications of this, specifically getting into planetary and gravitational concepts, and we'll do that in the next segment. All right, so the last little chunk of Chapter 6 is going to be dealing with a couple applications of centripetal acceleration and centripetal motion, and especially dealing on the planetary scale. We'll get into a little bit of orbits, we'll get into Newton's law of gravitation, but this part starts out with taking a look at a little bit of weightlessness. So there is a pre-lecture video. And this pre-lecture video, it's actually kind of cool. There's a lot of video of someone inside the International Space Station and this concept of what is weightlessness and how it's not actually being weightless, but actually constantly being in free fall. So we'll take a look at that in this section. So getting us into a couple of the applications, we're going to start by talking about orbits and weightlessness. So orbital motion, the concept of orbital motion is actually originally a Newtonian thought experiment. And his experiment, or his idea was, well, if I'm on Earth and I throw something, it follows this projectile path and it hits the ground. But what if I threw something high enough up, or from high enough up, fast enough that the shape of the projectile actually followed the radius of the Earth? So we're taking this concept right here and just zooming it out because we're going so fast. And this gets us into orbital motion. When we fire a projectile, the force of gravity pulls that projectile downward towards the center of the Earth. If I could launch it fast enough, which turns out to be right around 8,000 meters per second when we're at the Earth's surface, there becomes a point at which the curve of this projectile matches the curve of the Earth. And it becomes parallel to the Earth. We call this closed trajectory because it is a closed trajectory. As it goes all the way around, it comes back around to the original point. It's at the exact same point. So we call that an orbit. An orbit is the path that an object follows, or the trajectory of an object orbiting the Earth. And the concept is that there's actually always a weight force pulling it down. So something that's in orbit is actually constantly in free fall. So if we actually think back
to the forces that are going on in this, then there is weight. Weight is the only force bringing it down, but that equals mv squared over r. So we have mg equals mv squared over r, or a is that that centripetal v squared over r, and that's the speed necessary to maintain orbit. And if we solve for that, we actually get the velocity of the orbit is the square root of gr. Now, this should actually look extremely familiar. We just said that this is the critical speed of someone who needs to make it around a half pipe. And if I think about it, a half pipe is essentially a type of orbit. It's just a little different. It's working on the inside of a loop versus the outside. So the velocity of the orbit is also the square root of gr. Now, an important thing to note, though, it says the velocity must be square root of gr. It can only be the square root of gr. If we're going too fast, we actually sling out. We're going too fast that our velocity is not brought back down by this weight force, and we will escape orbit. So there's some important implications that'll come up with that. So taking a look at Earth's surface, if we were to orbit directly at Earth's surface, we can go ahead and plug in g and the radius of Earth, and we get around 18,000 miles per hour, or 7,900 meters per second, at the Earth's surface. So that is directly at the Earth's surface and how fast you would have to go to orbit the Earth. We can also use this equation to calculate the period and how long it takes at any point around or outside of Earth's surface, so we can manipulate that radius and figure out how long it takes to orbit the Earth as well. So taking a look at that concept, the period of an orbit, currently right now, there are about 3,700 man-made satellites that are orbiting Earth. And out of that 3,700, 1,100 of them are active and 2,600 are inactive. Or they're in what they call in orbit. They're further away because they're just meant to sit there. It's called a graveyard orbit. And we'll take a look at a video that deals a little bit with satellites. A quick thought about why satellites are placed where they are. It's kind of interesting. Like, if you think about, if you're sitting on Earth, that's sure, why not? That's Earth. And here's your country. That's not America, and there are you. Now, if you want to watch like satellite TV, there has to be a satellite. I don't know how to draw a satellite. There has to be a satellite orbiting Earth that can constantly send you electromagnetic waves to your satellite dish so that you can watch your HBO or whatever. So this satellite actually orbits then, as it goes around and comes back around the Earth, it'll actually orbit with you. And that's a concept known as geostationary orbit. That means as the Earth rotates, the satellite orbits at the exact same velocity. So it's got to be some distance away from Earth, and this picture is starting to get just better and better. It's got to be some distance away from Earth that it's constantly in line of sight with you. And that's a huge application that's used all the time, known as geostationary orbit. So we're going to watch this video. It's a little bit about launching satellites, a cool little video, and they'll also talk a little bit about the concept of what happens at the end of the satellite's life. This is an interesting video about SpaceX. SpaceX is essentially it's a company that puts satellites into orbit as like a service for hire, I guess you could say. And this particular object here, this is actually the launching mechanism that gets the satellite into orbit and with a fast enough velocity. And this whole video, this company has been working on re-landing these launch vessels so that they can be reused over and over again. So this is actually a sea platform. It's in the middle of the ocean, and it's designed to go and pick up the satellites. So this thing launches into space, essentially, and then does a controlled re-entry and comes back down so that it can be reused. So this company is a front runner in all this stuff right now. Nobody else is doing anything like it, and they're really popular, really interesting company. They're also the ones that are looking to plan that mission to Mars. So we could check this video out as well. This is actually, if you're bored, this is a full webcast that they did. The full process to launch a satellite. This is known from the Falcon 9, which was just another SpaceX, I believe, process of going through. So you can check out it is SpaceX. You can check out a full launch of a satellite and getting it into orbit from start to finish. This is an interesting little map of Earth's, or a graphic rendition of Earth satellites. You see that we have all these satellites that are concentrated around Earth, and those satellites are in geostationary orbit. And then we have all these other ones all over the place. And some of these satellites are actually being used, but the vast majority of them are actually dead satellites that we just kind of launched off into space because we were done using them and they were running out of fuel. And these will all one day, since they're within Earth's gravitational pull, they will all one day go through this process known as orbital decay. So if I were to imagine this satellite right here, it's orbiting Earth, but it's as it encounters more drag, eventually it'll crash into Earth. Hopefully it'll burn up upon re-entry, but all these satellites, all 3,700 of them, one day will crash down to Earth. So got a quick check. Astronauts on the International Space Station are weightless because, well, the space station is orbiting Earth, so it is constantly in free fall around Earth. There's no normal force, so there's no apparent weight, and that's why they feel weightless, but they are constantly in free fall around Earth. Another interesting thing that SpaceX is working on is they're trying to do a mission to Mars. And that is a one-way ticket, but the concept is, settling on Mars, making it an inhabitable planet, because one day the Earth's already getting crowded in some areas, but so what's the next frontier? So SpaceX is actually working on getting a mission to Mars, and you can go and train and go to Mars. So if you're interested, go to Mars. This is an interesting little video about working out in space. If you actually ever go to space, especially, there are some people now analyzing whether or not a trip to Mars is possible for the human body. And one of the big things is because there's no gravitational force, your bones actually go through this decay process similar to osteoporosis, but in a much accelerated time. So this video is from Smarter Every Day. This guy gets to go check out a lab that deals with astronaut stuff. And if you look at this, it might not look like much to you. That's pee. That's urine. There's a lot of it in that one. This is all astronaut urine, and they do a burning chromatography process to analyze and understand what's actually being just wasted through your body as you're in space. And he also talks about how they work out in space to try to negate those concepts. But yeah, if you're in space, because of the lack of gravitational force, or you're always feeling weightless, your bones actually start to essentially break down and decompose as you're traveling. So you age terribly when you're in space. So if you're going all the way to Mars, you got to know how to fight that and how to have that artificial gravity or some way that you can work out. So this video goes and talks about how you can work out in space. And that's actually all we're going to introduce right now. The next concept that we'll get into is talking about Newton's law of gravitation, which gets us further into the planetary talk, as you will. Astronomy is not actually within the scope and sequence of this class, but there are a couple of concepts that are. So we'll take a look at Newton's law of gravitation in the next segment.
Okay, so the next section in Chapter 6 is getting into actually a pretty important concept that does pop up a lot on the AP exam, and that's Newton's law of gravitation, or Newton's law of gravity. So before, we've talked about the gravitational force as being the weight, and that's just simply mass times gravity. Well, we're going to talk into a little bit more this unit, or this section, about where this G comes from, and also how your weight can change on other worlds, getting into Newton's law of gravity and where that concept comes from. So gravity itself obeys what's known as an inverse square law. So there are two things. So anytime that I have two objects that are near each other, they experience a gravitational force. And this might seem kind of weird, but it means that any two objects, if they are near each other, they will attract each other. So there's always an attractive force between those two objects. The force of mass 2 pulls on mass 1, and mass 1 pulls on mass 2. Similar, when you're on the Earth pulls on you, and you pull back on the Earth. So there is an action-reaction pair. But the things that matter, first off, the force is inversely proportional to the square of the distance between the two objects. So if I look at my formula here, this r squared value is on the bottom. That's saying that the further away I get from something, the less I feel its impact. And the perfect analogy of this is thinking about like magnets. So when I have two magnets really close to each other, they're either very attractive or very repulsive. But when I get pretty far away from each other, there's a very little effect that they have. Similarly, two objects that are very far apart from each other don't pull on each other as much as two objects that are very close. The other thing is that the force is directly proportional to the product of the masses. So right here I have M1 and M2 multiplied by each other. And the heavier the mass is, the more they pull on each other. So when you think about it, to kind of sum this all up, the Earth and the Sun exert gravitational forces on each other. So the Earth pulls on the Sun pulls back on the Earth, and that's what helps us orbit the Sun. And we'll talk more about that a little bit later, but at the same time, the Sun doesn't pull me off the Earth because of how close I am compared to the Sun. So that r squared factor is a thing, as well as the masses. And also when I jump up, I don't feel the Earth going up as much because of its masses. So let's take a little bit further or a deeper look into this. And we'll do that with an example problem. It says you're seated in your physics class next to another student that's 0.6 meters away. Estimate the magnitude of the gravitational force. Assume that you each have a mass of 65 kilograms. So the gravitational force, that's the attractive force, always attractive between two objects. Later on in the year, we'll talk about Coulomb's law. And Coulomb's law is a little bit different. That has to do with electric forces, and it's a very, 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 very similar formula, but it's just a little different because we're dealing with charges, and charges can be attractive or repulsive. But for us, this is just attractive. So it's G, which is Newton's gravitational constant, is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of the first student, which is 65 kilograms, times the mass of the second student, which is also 65 kilograms, that's right around 130, 140, 150 pounds, divided by this 0.60 meters, and of course that quantity is squared. So that's all we're saying. We're saying that when I have two masses next to each other, there is a force that's bringing those two together. And if I quantify that force out, I get about 7.8 times 10 to the negative 7th newtons. And when I think about that, that is 0.1234567 newtons. Wow, that was funny that it had 6, 7, 8. Anyway, the force is essentially immeasurable. It's too small to actually cause an effect, because then if I look at, acceleration equals force divided by the mass, if I look at this really, really small force divided by your mass of 65 kilograms, that's going to be even 100 times smaller. So it's just, it doesn't cause enough based on our masses. But when we get into the masses of planets, it absolutely causes more than enough. This is a stupid video. I just love it. Can a person have their own orbit? Kind of is the answer to this question. This is a Family Guy video of when Brian, who's, in case you don't know, Brian's the dog. Oop, I don't know why that. Okay, Brian's the dog. He starts throwing objects to Peter, and they start orbiting him. And the reality, of course, would be that doesn't happen. And the reason that doesn't happen is because we are not, as people, we're not the sufficient mass in our system. The Earth is. So that's why the TV would fall down, the apple would fall down, but it's just a stupid, funny little thing. But if I were in the middle of space, in the middle of nowhere, I could potentially have the dominant mass around, and maybe then I could have my own orbit. All right, so I got a quick check. The force of planet Y on X. So planet X is 2m, planet Y is m. There's some distance apart, and there's this force of X on Y. And my question is, what about the force of Y on X and X on Y and how they relate to each other? They are going to be the same. And the reason they are the same is this is Newton's third law. Planet Y pulls on planet X pulls on planet Y. This is an action-reaction pair. This is Newton's third law, so they experience the same force. Another quick check. Here I have gravitational force is 1,000,000 newtons. What will the force be if I double the distance? Well, if I look back at my formula, it's Gm1 m2 over r squared. So if I double this distance r, it's going to be 2 squared, so it's going to end up being a quarter of the force, and that'll be 250,000 newtons compared to the original 1,000,000 newtons. So on other planets, I can use this concept of gravity and Newton's law for gravity. So the weight on the moon, for example, I could calculate that, how much you would weigh on the moon. On Earth, the weight is mass times gravity of Earth. On the moon, it's mass times gravity on the moon. Well, if I set this force of the moon equal to mg, right, then actually these two, this little m right here, that's the mass of me, this is the mass of me. Those cancel, and then I get this formula that the gravity on any planet ever, anywhere, is based on still that Newton's gravitational constant, the mass of the planet, and the radius of the planet squared. So this is actually how astronomers and astrophysicists use data that they have to calculate free fall acceleration on other worlds. They can figure it out just by using this actually really simple equation, and then they can make accurate predictions about, for example, if you're gonna do a flyby with a satellite, and that's a huge concept. If you look into the history of astronomy, there are countries that have launched satellites into towards Mars and stuff, and they'll miss Mars because they don't properly account for, first off, the trajectory of the satellite, which is really hard. If you're thinking about launching a satellite to Mars, you're talking about where it's you're aiming at a target and where it's going to be in 9+ months. It's a really difficult thing to do. You're not aiming at a bullseye. You're aiming at where a bullseye is going to be millions of miles away in thousands of days. Okay, so it's really tough. But also, if you don't correctly account for the free fall acceleration, the gravitational pull of the planet won't be strong enough if you're not close enough, or it'll be too strong because you're too close, and it'll either not pull the satellite in, or it will pull the satellite directly into the planet. And then in either case, you can't launch a satellite into orbit around that planet. So really interesting things or issues that we have to tackle if, in fact, we do ever want to colonize Mars. So here's a quick little conceptual example, not that I got off track at all in the last 2.5 minutes. Calculating G on Earth, if I plug in Newton's gravitational constant and the mass of Earth and then the radius of Earth, I get a free fall of Earth of 9.518 meters per second squared. And you're saying, wait a second, free fall acceleration on Earth is 9.81, or depending on your belief system, 9.80 meters per second squared. Why is this 9.518? Well, I would say that it's close enough. And the reason is, of course, we have the mass of Earth to the nearest, well, I mean, if it's oh, you're going to hate this one. 5.972 times 10 to the 24th kilograms. That's I'm sorry, I'm going to get rid of that point. 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 kilograms. Okay? You see how this is a problem? If this is off, if this whole line of zeros is approximated, that's a really long line of zeros. And of course, the same thing with the radius, that's going to lead to some type of round off error. But 9.81 or 9.8 compared to 9.5, yeah, that's close enough. All right, another quick check. 60 kilogram person stands on each of the following planets. On which is the weight the greatest? Well, your weight is, of course, mass times gravity. And that's your mass times gm over r squared. So if I were to evaluate 2r, 2m, 3m, 3r, so this is m over r. So my g is going to be 1 over 1 squared, which is, we'll call that 1. In the second one, I got 2 over 2 squared, so that'd be 2 over 4, which is a half. And in the third one, I got 3 over 3 squared, which is 3 over 9, which is a third. So I'm going to weigh the most, actually, on this planet. Now, you might say, wait a second, that doesn't make sense, because Jupiter, I would feel really, really heavy. And in fact, Jupiter does have a free fall acceleration of, I believe, around 27 meters per second squared. And the reason it is because this mass right here, it's dense. Jupiter is a dense planet. Physicists believe that if Jupiter was just a little bit more massive, it would have become a sun and not a planet when all the mass came together. So you're talking a significantly different amount of mass, and that's why it has such a higher free fall, and that's why we would feel really heavy on Jupiter. Anyway, that's your quick little introduction into free fall acceleration and where it comes from. The next thing that we're going to take a look at is an application of free fall acceleration, and we'll talk about gravity and orbits and how they impact one another, and we'll do that in the next segment.
All right, we got one more section to go through in Chapter 6, and it's all about an application of the previous section, which was on Newton's law of gravitation. So gravity and orbits are taking a look at combining some of our concepts together, and this should be a pretty quick video on it. All right, so the first thing that we're going to take a look at is taking a look a little bit closer about gravity and orbits. And we've talked about this a little bit, but anything that's in orbit, such as this satellite over here, it's around some larger mass, and it has to have some velocity to keep it in orbit. And the thing that we talked about is that it doesn't have to have a critical velocity, but it has to have a specific velocity in order to maintain its radius. Too fast, too much velocity, and it flies away because the quote-unquote centrifugal force is too large. Too little velocity, and the gravitational force will win, and it'll crash into the planet. So if we set our g m1 m2 over r squared, which is Newton's law of gravity, equal to our mv squared over r, we get one of the r's do cancel, and the velocity needed to obtain that is known as the orbital velocity. And that's an orbital velocity that's specific to any planet and the radius away from the center of the planet. So actually, I talked about this before, but the velocity to have an orbit before equaled the square root of gr, and I said, well, that doesn't really necessarily make sense, because if I increase the radius, that means I have to go faster. But actually, when I take into account Newton's law of gravity, the further away I am from the planet, the less the gravitational force, the slower I actually can go to maintain that orbit. So this is known as the orbital velocity. It's just an application of gravity in orbits, but that's the exact velocity that any satellite needs to be in order to orbit a planet. There's a couple different things we can evaluate with that then, with that formula. We know that it's the square root of gm over r, where g is, of course, Newton's gravitational constant of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. You got that one memorized yet? And we could set that equal if we were to take a look at what velocity is. It's distance over time, or in this case, it's their circumference over the period. And if we set those two equal to each other, we get this other random equation that just relates the period of a satellite to its radius with this 4 pi gm in the middle. That's going to be a constant. So just another quick little application that we can have. So quick check here. Two satellites have circular orbits with the same radius. Which has the higher velocity? So we just said that velocity is the square root of gm over r. And this mass is actually the mass of Earth. So actually, when I have two different satellites with different masses, they're going to have the same speed. Mass of the satellite doesn't matter. And if you recall, that's because we set gm m, where m is the mass of the planet, little m is the mass of the satellite, over r squared, equal to mg, and the little masses cancel. So the mass of the satellite does not matter. So here we have another quick check. Which one has the higher speed? And again, going back, v equals the square root of gm over r. The one in the smaller orbit, the one that's closer to the planet, radius is on the bottom, so as r goes down, velocity will go up. So the one in the smaller orbit has to go faster in order to maintain and overcome that gravitational pull. Right, another quick check. A satellite orbits the Earth. The space shuttle crew is sent to boost the satellite into higher orbit. Which of the quantities increases? Well, so we're assuming that it keeps the same velocity, and we're just pushing it out. So we can get rid of speed, and if I think about angular speed, then that's how many rotations it makes. So it's going the same speed, but it's traveling a greater distance. So that's actually going to go down. The centripetal acceleration is v squared over r. Radius is increasing, velocity is staying the same, so that's not right. And the gravitational force, well, that's gmm over r squared. I'm increasing that, so that's actually I'm increasing the radius, so that's actually decreasing that as well. And the period is the only thing that is going to increase. It takes longer to go around if it's going a greater distance at the same speed. There is one quick application that I always like talking about with this, and that's this concept of geostationary orbit. And I talked about this in class, but many of the satellites that we use, they don't actually, they appear, I should say, to hover over one spot outside the Earth. So when you rely on satellite communications for things like TV, the satellite's not moving relative to us. So it's known as being in what's called a geostationary orbit. And a geostationary orbit means that it rotates simultaneously with the Earth. So the Earth takes 24 hours to go around. The satellite takes 24 hours to go around. So if I want to solve for how far away I need to put the satellite from the Earth, I can plug in a period of 24 hours, which is 8.64 times 10 to the 4 seconds, into this special case equation that I derived previously. And if I solve for the radius, I'm going to take the cube root of that, so that ends up right there. Plug everything in, and it's 4.22 times 10 to the 7th meters. So that's how far away from the center of the Earth. So then of course I have to subtract the radius of the Earth from that to figure out its altitude. Astrophysicists do this so they know exactly where to place satellites in orbit, so that they're orbiting at the same velocity of the Earth. So it's a pretty important application of gravity in orbits. But that actually does finish up Chapter 6 for us. So just a couple quick little applications, a couple quick little cool little formulas, and that's actually going to be it for dealing with Newton's law of gravitation and uniform circular motion. We will come back in second semester and we'll take a look at rotational motion, which is going to be a little bit different, but it has a lot of the same concepts that we talked about right now. But that's it for now. We'll see you in the next chapter.